All right, I can see your PowerPoint if you'd like to go to full screen.
Beautiful.
Yeah, that looks good, Tim. Do you want to advance a few slides just to make sure we can see? Perfect. All right, you're good to go. Thank you very much.
Great. I'll just minimize the slide thing.
I also want to just remind all the students to change your name in the Zoom interface to reflect your sync group assignments, sync group 2.
Tim, this is Amitabh. Good morning and thank you for preparing your talk. You also kindly sent us some movies. I just want you to know that the version that is posted is a PDF version of your talk without animation. And that's what we have been doing with all our presentations so far. Hope that's all right with you.
Yes, that's fine. Yes, I mean, if you want to update it with the animations at some point, you can, but that's fine, of course. Can you hear me okay? Is everything working well?
Totally fine, and thank you very much.
Good. Okay. So shall I get started?
I think so, Tim, because we have to keep on time and there will be questions and so on and so forth.
Good. Okay. So I'll talk till, well, we'll have a break at 8:20, I understand, for 10 minutes. So I expect you've heard a lot about space weather from people like Bill Murtaugh. So my job is to dig in a little bit on the space weather effects in the upper atmosphere, the thermosphere and ionosphere. And I'm based at SWPC. I'm employed by the University of Colorado, but based at SWPC, the Space Weather Prediction Center, which is the nation's provider of space weather information, the official provider. So I'm very much sort of aware of the need for the operational need or the needs of users for space weather products. So I've been trying to model some of these space weather products with physical models of the thermosphere and ionosphere over the years. Because most users, they don't just want to know what it is now, they'd like to know, you know, are there going to be ionospheric irregularities or negative phases of storms in, you know, over the next 24 hours or, you know, days if possible. And of course, that's a much bigger challenge. So you don't have to just observe it and say what it is now. You have to actually be able to understand it. You have to model in a physical model, understand the drivers, and then you can say a little bit about what might happen in the future. So that's always been my sort of goal working at the Space Weather Prediction Center. I expect you guys have been quite saturated with all of the information that you received. So I'll start off slow. So I need to go to the right. Yeah, just kidding. So I expect you heard a lot about the traditional space weather, which are the sort of the three main drivers from the sun. The solar flares, coronal mass ejections, and solar proton events. And I expect Bill has sort of talked a lot about this type of thing. Of course, the solar flare is an increase in the X-ray flux. And of course, it's an increase in a broader part of the spectrum than just the X-ray flux. But that just happens to be how we observe that solar flare X-ray increase on the GOES satellite. Of course, just the speed of light to get from the sun, but that doesn't give us much warning, of course, because by the time we know it's here before when we realize that it's actually happened. So it doesn't actually give us any warning, and they can last a day or two. So an hour or two. So they're very short-lived, and of course they penetrate down into the D region ionosphere, and they impact high-frequency communication, HF communication through absorbing the radio waves. It can affect geolocation, any HF user. There is some old low frequency navigation systems, and it doesn't really have much of an impact on GPS, but in principle, if they were big, you could do. Of course, the coronal mass ejection, the plasma coming out from the sun, that I'm sure you've been talked about or heard about, takes a day or 1 or 2 or 3 days to get to the Earth, and it can last for a day or two in disturbing the upper atmosphere. And of course, that drives a geomagnetic storm, and of course, there's other things out in the magnetosphere with satellite charging, satellite drag, and of course, all the communication and navigation effects. And again, HF communication. And solar proton events, the energetic particles, they can arrive as quickly as 15 minutes, the relativistic motion. But they can take a few hours as well, and they last for much longer, so they can last for a few days, so they have a sort of a longer duration impact than solar flares, but have a similar effect of ionizing the D region and causing absorption. So they're the 3 traditional measures, and of course there's the NOAA scales that I'm sure you've probably heard about, the radio blackout scale, the R scale, the solar radiation storm scale, and the geomagnetic storm scale, the G scale. And that gives you an idea at the different levels, just like the hurricane scales give you an idea of, whether it's minor, moderate, strong, severe, or extreme. So there's a lot of useful information about some of the impacts on these traditional solar drivers of space weather. So these are the list of, the solar flare, solar proton events, and geomagnetic storms, or CMEs, are sort of the traditional drivers. There is something with solar radio bursts. If you have a cell phone tower and your line of sight between the cell phone tower and your cell phone lines up with the sun, and there happens to be a solar radiation burst, then there'll be interference in the communications. But it's because there's so many other ways that often cell phone signals go, then it often doesn't actually cause big problems. So I'm not going to focus very much on the solar radio bursts. But if I have time towards the end, I will talk a little bit about another source of space weather that hasn't really, it's a bit of a new paradigm. And it's the effects of the waves propagating up from the lower atmosphere. And we found that they probably triggering ionospheric irregularities, and they're creating undulations in the ionosphere affecting HF. So hopefully I'll be able to get to that. If not, I'll maybe talk a little bit about it a bit tomorrow when I talk a bit more about the thermosphere and ionosphere. So let's go. So some of the upper atmospheric space weather impacts on operational systems. The first one in the thermosphere is the neutral density, and of course satellite drag in low Earth orbit, and for the space traffic management and orbit prediction, conjunctions for predicting conjunctions and for collision avoidance, and re-entry in the lower parts of the thermosphere. So for that, we need to understand the neutral mass density and somewhat the winds, because the winds affect the drag if there's a headwind or a tailwind, and sometimes the winds in the upper atmosphere can be up to a kilometer per second. So they can modulate the drag effect, but the main effect is the heating and the thermal expansion. And of course, there's structure and waves that affects objects with high area to mass ratio that are much more impacted by blobs and structure in the neutral density. In the ionosphere, the impacts on radio wave communication, of course, the HF, that 3 to 30 megahertz range, as we talked about, the solar flare and solar proton events can enhance the D region that absorbs the HF signals. And of course, you need a layer to, are you able to see my cursor when I move it on the screen or not?
Yes.
Okay. So of course, for HF communication, you need a reflecting layer to bounce the wave off that layer. And so and then the signal refracts through that layer. So any structure and gradients or undulations in that F region layer are gonna scatter those signals and redirect it. So we need to understand that structure as well as just what the the plasma density is at those altitudes, so that the wave does actually reflect, so you can communicate at distance. With the global navigation satellite systems, and of course GPS is one of those, there's used for precise point positioning, satellite navigation, and timing, PNT. And of course the GPS frequencies are up at the gigahertz range, 1.5 and 1.2 gigahertz. And of course the line of sight from the satellite to a user will cause a delay. If there's plasma there, it'll cause a delay on that signal, and it can refract the signal, just can bend it due to the structure. And if you have blobs, patches of irregularities, then that can diffract the signals and cause the amplitude and phase scintillations, the strength and phase of the GPS signals. And sometimes, of course, the fluctuation can be so bad that you get a complete loss of the signal. So, and then, of course, the satellite communications generally, the same plasma irregularities are going to cause the scintillations and loss of signal. So that's sort of why we need to understand the system. I keep pressing the wrong button here. So some of the atmospheric parameters affecting the radio wave propagation, of course, we have the D region from the flare and the polar cap absorption affecting 8 for polar cap enhancements of the D region affecting HF absorption. We have the F region peak density that we need to reflect the wave from, and any bottom side waves and undulations are going to affect the HF propagation. And geolocation, geolocation is trying to work out where a signal has come from based on a set of receivers. And so you need to understand how the signal is reflecting off all the undulations in the bottom side F region. The negative phase ionospheric storm, so the maximum usable frequency that you could use if the F region has been depleted, and that same wave that would normally reflect and you can transmit to another ground, to a receiver on the ground, that signal then just passes right through the ionosphere and doesn't get reflected. So we need to understand where there might be these depletions of the ionosphere, because that affects the maximum usable frequency. And of course you might have positive phases and geomagnetic storms, which is increases in plasma density, and that's of course great for the maximum usable frequency, because you can use a higher frequency. But sometimes the positive phases are associated with structure and irregularities. And so then that is then going to impact your satellite signals and range delay and things like that. And any ionospheric gradients and structure are going to cause diffraction and scintillations in the signals. So these are some of the things that we need to understand. So if we sort of go through what we might see with a solar flare, this is just, I think, what was roughly in the first slide. So the increase in the X-ray flux that's measured from the GOES geostationary satellite. It's the 1 to 8 angstroms, or 0.1 to 0.8 nanometers. That's the wavelength that the GOES satellite actually measures. The wavelengths, a broader part of the spectrum is actually increasing. It's just that we're using that as the index for the flare. Of course, the neutral atmosphere has a small cross section for the X-ray photons, so they can penetrate deep into the atmosphere, get down to below 100 kilometers altitude, where they ionize the D region, and then a radio wave passing through the ionosphere. You get absorption of the HF radio waves in the D region. Of course, the arrival in 8 minutes, but not really, because it's already here when you know it. And the flare duration is an hour or 2. And there's a lot of users that still are using HF communication, particularly FEMA uses it a lot for disaster response. If there's been a hurricane and you're losing a lot of other communications, maybe cell phone towers are out and things like that. So there's still a lot of demand to maintain a HF communication capability. So if you can imagine that for vertical propagation, if the wave just goes up and straight reflects off the ionosphere, the radio wave will reflect when the plasma density matches the radio wave frequency. So there's a relationship between the frequency and the plasma density. There's just this scaling factor. And the peak plasma density is usually referred to the NMF2, the peak F region, the F2 region, which is the peak, or the layer where the maximum plasma density occurs, which is usually at around 300 kilometers. So you can see if you just reflect from that layer, you have a communication distance for out to 500 or maybe 1,000 kilometers on a single hop. Of course, when you're using an oblique angle, the radio wave encounters, as the radio wave encounters the denser plasma, it'll refract. So you can actually use a higher frequency, and so then you can have, high frequencies mean less absorption. So you can use maybe 30 megahertz, maybe the 10 megahertz might be what would be for a vertical propagation and reflecting vertically off the peak plasma density. But if you're at a certain angle, you can use a higher frequency. And then you get the apparent reflection from the F2 layer from the diffraction, from the refraction as it passes through the layer. And that reflection layer is usually the F2 layer. So that tells us what the maximum usable frequency that we could use for a given skip distance and for a given F region plasma density. And the higher frequencies, that they are good because they suffer less absorption. And of course, when we talk about a radio blackout, it's a bit of a misnomer in the ionospheric scales. It doesn't black out, it only blacks out the HF, and not always that, of course. So it's not all radio frequencies. So radio blackout is a little bit of a misnomer. So just the idea of this usable frequency window, you have to use a frequency that obviously you want it to reflect off the F region ionosphere. So that tells you what the maximum usable frequency. If you're too high, it'll just go right through. So you need to be below a maximum usable frequency for a given angle and a given F region plasma density. And as the plasma density increases during the day, you have a sort of a diurnal variation that is shifted a little bit in local time so that it goes off into the night side. So the peak is sort of in the afternoon. So this is sort of reflecting the diurnal variation of the MOF, maximum usable frequency. It's reflecting the diurnal variation of the F region plasma density if it's nice and uniform and smooth. And the lowest usable frequency, if you use a frequency that's too low, then there'll be so much absorption in the D region that there won't be enough signal when it gets to the receiver at the other end of the propagation path. So you have this usable frequency window. And if you have a flare, then the lowest usable frequency, you can't use such a low frequency anymore. So you have to use a higher and higher frequency because there's too much absorption. And eventually, if you have a big solar flare, you can have a complete shortwave, what they call a shortwave fade, so that you're completely closing the communication window, and then you have there's no frequency that you could communicate with, because they're for the frequency that you would need to use to get you to your destination would be so high that it would actually pass through the F region and be lost. So you completely wipe out that frequency window, that communication window.
Tim,
yes.
Before you go ahead, if I may just make a remark to the students, if you would like to ask a question, as you well know, you're welcome to raise your hands or send me or everyone else a quick chat message that I can bring to Tim's attention. So far, so good. There have been no such requests. but just to let you know, the standard protocol holds for this talk as well. Thank you, Tim.
Yes, totally. And yes, I agree. Yeah, so the product, the D-region absorption product for the solar flare at SWPC uses the GOES X-rays as the driver and shows the region on the day side that would be affected by the solar X-ray, and it gives you the amount of absorption, the attenuation, or the frequencies that would be attenuated. So that's the product that we put out to try that. And of course, it's just tells you what it's like now. It doesn't give you any forecast. You would need to forecast the X-ray flux in order to say what it might be in a few hours. And it has a certain time constant. So you have an estimated recovery time on that. So that gives you an idea of, and this is well used by the International Civil Aviation Organization. They want to know if there's going to be communication problems, and FEMA and any emergency managers will be monitoring this type of product from SWPC. So I wanted you to just think about a question, and then we'll come back to if we give any, you can put answers in the chat. Just you could just have one or two word answers if you want, and we'll look at that when we get in a few minutes. So the question is, why does the D region absorb the radio wave when it has the lowest density compared with all the other ionospheric layers? Why does the absorption not maximize in the F2 peak? Why is it the D region that is creating the absorption, and not the E and the F region, which have much higher plasma densities? Because even during a flare, the D region enhancement doesn't reach even the E region plasma density. So have a think about why it's the D region that absorbs the radio wave and not the E and F region. And we'll, if you want to put answers in the chat, that would be great. And we'll come back to that in a few minutes. So what would an operator see if he was, this is in sort of the Midwest in the US, so I forget where it was now, Kansas or somewhere like that. So the UT is at the bottom, and we're showing the signal strength for communication over a distance of about 500 kilometers or something like that. So we have the propagation up to the F region down. So again, if you remember, we need to use a frequency that gets reflected off the F region, otherwise we won't have a signal. And this is showing the signal strength. So if it's low, it means that it's either been absorbed or it hasn't reflected. So you can see the periods, and there's two lines on here. One is the red, which is the average of the last 5 days. And the blue is this particular night. Every six minutes, there's a data point. So you can see that at dawn, the plasma density, you can see there was no very little signal at night, and so obviously there'd be no D region absorption at night because it's not illuminated by the sun. So the reason why it's not being you're not getting a good signal is that it's not reflecting off the F region. So from about 4 UT to about 12 UT, which would be close to sunrise in the middle of the United States, then there was no signal because there was no reflection off the F region. Then eventually the F region is rising, and then the signal then starts to propagate, and you see a signal, and then this region you have an absorption. The D region starts increasing, so that on the 5-day average you can see that this day side absorption, so that there's still a signal getting through, but the intensity of the signal is decreased. And then it stays on through the night, and then eventually the F region depletes, decaying away during the night, and eventually it'll cut off at some point. In here, in this case, it's at 4 UT, so it would be about sort of just before midnight. local time. So somewhere on here, there's a solar flare. And if we click to the next one, we can see where that flare, but so this is the sort of thing that an operator would have to deal with, and understanding, you know, what frequency should I use? You know, what's the cause of the problem? Is it an absorption effect? Is it, I'm not reflecting off the F region, or is it a flare? And the flare is this feature here. You can see it starts to come up, and normally it would you would just have the normal absorption, gradual decrease, but it suddenly drops down. So this would be the signature of a flare, but it's quite hard to see with all these bumps and wiggles, and of course there's structure in the F region to really tell that that's, you know, it would be hard for a user. So if you've got some information about the, that there was a solar flare, then it's very helpful for communicating a community, an HF communicator.
Tim, there's a question in the chat channel. Is the absorption higher in the D layer due to a higher neutral density?
Yes, I will. Yes, let's just sort of, I'll come to the answer to that question. But yes, you're obviously on the right track there. Yes, it's the neutral density. So yeah, but let others sort of put in their thoughts on it, and then yes, I'll in a couple of slides we'll look at some of the answers and then explain the reason.
Thank you, Tim.
And as I said, of course, the 1 to 8 angstroms isn't the only part of the spectrum that increases. Sometimes the EUV part of the spectrum increases during a flare, and that energy gets absorbed higher up in the thermosphere, up at about 200 or 300 kilometers altitude. And there you can actually see the neutral density response. You get about a 50% increase in neutral density because the EUV heats the upper atmosphere. And so this is a flare. And then you can see the neutral density observed from a satellite, and an accelerometer on a satellite up at about 400 kilometers altitude. And here the recovery is much slower, whereas in the D region will just follow the time sequence of the solar flare. There's an example in the bottom right there of the time sequence, and the D region will follow that. So the HF absorption recovery will be rapid as well. But in the EUV part of the flare, which can occur, and there's not always a one-to-one correlation between the X-ray flux and the EUV flux during a flare. But if you do have an EUV flare, then it will get absorbed at higher altitudes, and you'll see a neutral density response, which in principle could affect satellite drag. 50% increase in density is significant. Excuse me, I'll just have a sip of water.
Tim, while you're taking a sip of water, I always struggle to read these plots.
Oh, okay.
So we're looking at.
Yeah, this is each vertical stripe is an orbit, or an average of a few orbits, and it's going from the South Pole to the North Pole, and you can see depending on the local time that it's sampling, and here it tells you that local time is 13 local time. So this would be the day side increase in density, and then the high latitude region is lower density. So it will go through a peak, and then it will go at low latitudes, and then it will go through a minimum again at the pole. So these are all the day side orbits, and you just collect them all up over this is how much? This is a 2-day period. And so you can see when the flare hits on the day side, the neutral density suddenly increases, and then it's slowly decaying, and it's gradually recovering, and there's still a remnant of it even you know, a good 12 hours later. Does that explain the figure?
Yes, I think I get it now. And so the first figure is in the summer, the Northern Hemisphere summer, and the second figure is near one of the equinoxes. Is that? No, they're both at the
They're
same.
both the same. They're both the
same
same
time.
event.
Okay.
The one on the right is a different satellite. This is the CHAMP satellite that happened to be at 13 local time, and the GRACE satellite happened to be at 16 local time. So there were just different parts of the diurnal variation. So this is closer to the peak. You can see slightly higher densities at CHAMP. And some of it some of it are actually the altitude change as well. I don't think these have been normalized to a same altitude. So the GRACE is at higher altitude at 490 kilometers versus 400 kilometers for CHAMP. So some of it is the altitude change.
I wanted to just mention, you said this, but I want to make contact with stuff we've discussed in the school, that the effect here is that the temperature of the upper atmosphere increases, and that increases the scale height of the atmosphere. And that means that at any given altitude above where the energy is absorbed, the density is higher. Is that basically the
Yes,
how it is that a flare is increasing density?
Yes, that's exactly right. Yeah, we can think of it as a thermal expansion. You heat something up and it expands. And at the site of the heat source itself, an expansion actually gives you a reduction in density, believe it or not. But if you're one scale height above the heat source, and if you have a very spread out heat source, there'll be plenty of heat beneath lower altitudes, that then you'll see the density increase because of the thermal expansion of the whole atmosphere. And I'll talk a little bit more about the drag effects and thermal expansion in a little while.
All right, thank you. Yeah, that's very interesting.
So just solar proton events is very, very similar, except now we're looking at the high energy solar protons, and they tend to be directed towards the polar regions and high latitudes by the Earth's magnetic field. As they're coming from the sun, the protons can't penetrate through the magnetic field very well, so they get directed into the polar regions. And depending on the particular shape of the magnetic field and how active the magnetic field is from geomagnetic activity, will tell you how far equatorward that cutoff latitude would be. And I'll show some pictures of that in a minute. And again, the GOES satellite is measuring those energetic particles out at geostationary orbit in that 10 to 100 MeV range. And the same for same as it was for X-rays, the energetic protons have the neutral atmosphere has a small cross section for those energetic protons. So again, they can penetrate deep into the atmosphere, where again they ionize the D region and cause the same absorption as for X-rays. Very similar effect. It's just geographically it's at it's at high latitudes. And this is the arrival time that we talked about and some of the users. So it's the very similar effect. Of course, the duration is much longer. You can see here the increase in these 10 and 50 MeV protons from the GOES satellite, the proton flux. You can see the rapid rise, and then they can last for several days. And so you could have absorption for a long period at high latitudes. And this image on the right, and the time history depends on how the source of the energetic particles is connected through the interplanetary magnetic field, whether you have a rapid onset and then a recovery, or a slower onset and recovery. It depends on the connectivity, the magnetic connectivity to the Earth, to where the source of the energization of the solar protons. And on the right, it gives you shows you the region where you have the cutoff, where you would have the absorption. So at low latitudes, you don't have the absorption because they can't get there.
Tim, can I ask a question?
Yes, of course.
So the top plot that you're showing, and you're showing, of course, magnetic field line, I believe. So is that connectivity kind of to the west limb of the sun? Because there are two different components, right? So we kind of look for CMEs that are face on, and then CMEs can dump a lot of energy, but the magnetic connectivity is coming from the west limb. Is that the case?
Yes, I think so. Yes, I think it's supposed to, the figure, this is an old figure and I'm not an expert in this, but if it's on the west limb, yes, the connection will be rapid. Whereas if it's more center disk at the time, I think where the source of the energization, then it will be a slower. So I think it's something like that, whether it's the west limb or center disk, where the source is. But I must admit, I'm not an expert in that.
Okay.
And so that effect is also included on our D-region absorption product, and you can see of course the left animation is showing the rapidness of the flare effect on the day side, but when you do have the solar protons, they're much more long-lived, and so you can have these bands at high latitudes where the absorption will overpower the possibility for HF propagation. And it's important because if you have polar routes, if you have a route over from Chicago, say, to Hong Kong, and there's lots of polar routes now because it's the shortest distance for a lot of the international routes, intercontinental routes. And there's a region around the pole where you don't have any other means of communication except for HF, because the angle to the geostationary communication satellites is too shallow, so that it's hard to communicate anything other than HF. So if you have HF absorption as well as the no satellite communication, which occurs above about 82 degrees north, you've got no HF either. So it means that the airlines, civil aviation, are not allowed to fly over a region where they know that they will not have communication. So they have to take longer routes, and that can be expensive. And they also, of course, it's a bit unnerving if you're flying through a region on an aeroplane as a pilot or as a passenger and you have no communication. So they want to know when there is going to be one of these polar cap absorption events so that they can reroute their flights. It costs them more, of course, but for safety issues, and there's actually regulation that they can't knowingly fly into a region where there's no communication. There's one piece missing in this product. There is actually you can have auroral absorption as well, where the energetic electrons, but these are KV electrons, but there can be a high energy tail for that auroral precipitation. There can be a band of absorption around the auroral oval as well, which isn't actually included on the D-region absorption product at the moment. And of course, that can cause scintillations as well because of the structure. Whereas the solar proton events, the flux is fairly smooth. There's not a lot of structure in the source when it gets into the polar regions, but of course the aurora does have a lot of structure. So now let's get back to that, the question. Yes, are there any more things in the chat? Can someone tell me?
There was one proposal about basically absorption due to scales of the variations matching the HF wavelength. Otherwise, people were talking about neutrals.
Yes. Okay. And it is the neutrals. It's I mean, because as the radio wave propagates through the plasma, if you have free electrons in the plasma, they'll start to oscillate with the radio wave, and then as the radio wave goes through, they'll re-radiate. So then the electron oscillations stop, and so as long as they're free to oscillate and then re-radiate, then the radio wave can propagate through the plasma. In the E and F region, the collisional frequency between those electrons and the neutral atmosphere is low. So the energy just stays in the wave. But in the D region, below 100 kilometers, the atmosphere is now very dense, so the increase in the electron neutral collision frequency is it's much higher, so that as the wave passes through, just during the time period that the electrons start to oscillate, they'll suffer some collisions with the neutral atmosphere, and that will take some of the energy out of the wave. So so the person that said yes, it's due to the atmospheric density, that is the case, and it's the electron neutral collision frequency that increases. So well done on that.
Tim, if I may
Yeah.
just interject, you are about 9 minutes short of the break, just to prepare you. So
Okay.
think of a good stopping point, if you will, after which there's a little break and we'll pick up the second session.
Sounds good. Okay.
Thank you.
So I'll just start to talk a little bit about the geomagnetic storm response before the break. And of course, that's the result from a coronal mass ejection hitting the Earth. And of course, you can have a geomagnetic storm from a co-rotating interaction region at low solar activity. But the big ones are usually coronal mass ejections. So they're driving a geomagnetic storm. Of course, it takes 1 to 3 days for that CME to arrive. They can last for a day or two. And they inject energy into the upper atmosphere, so they're going to cause heating and expansion and increase satellite drag, as we've just mentioned with the flare effect from the heating. And there's a disruption of HF communications, because you can have positive and negative phases in the F region affect the HF communication. And it can cause structure and irregularities that would compromise the GPS, PNT, the positioning, navigation, and timing. And of course, there's lots of things like induced currents that I'm sure you've heard about, and power outages and satellite anomalies that sort of a bit out of my field. But of course, a lot of things are going on during a geomagnetic storm that are affecting lots of different users. And of course, when the IMF is southward, the interplanetary magnetic field, when the CME plasma's arriving at the Earth, if it's southward, then it can connect to this northward Earth's magnetic field, and then you have a connection, and then you can connect that energy in the solar wind much more effectively into the magnetosphere and cause a lot more disruption in the magnetosphere, magnetospheric convection. So you want a strong southward IMF to get a big geomagnetic storm. So you get an increase in the high latitude heat source, and that's that magnetospheric convection and the auroral precipitation. And I'm not sure how much you've heard about magnetospheric convection, but I didn't plan to go into a lot of details with that. But the net result is that if you increase the aurora, you increase the conductivity at high latitudes. And if you increase the magnetospheric convection, that maps down into the ionosphere to give you ionospheric convection, plasma convection. And that creates a dual heat source. And the dual heating is the main heat source at high latitudes during a geomagnetic storm. The other magnetospheric source is this penetration electric field, which I'll talk about a bit later. But the main thing for is the dual heating. So the thermosphere response to these magnetospheric sources, as I said, you have the auroral precipitation and the magnetospheric convection. They're expanded and enhanced. And you're getting plasma transport at high latitudes. And you can, within that auroral transport, you can get scintillations and of course that auroral absorption that we mentioned. The magnetosphere, the penetration electric fields, when you suddenly enhance the high latitude electric field, that electric field can be seen globally, and that propagates to low latitudes, and that can cause plasma drifts at mid and low latitudes. So again, it'll reconfigure the plasma at mid and low latitudes and affect lots of things. It affects HF communication, plasma gradients, creates irregularities, and affects the communications and navigation. The motion of the plasma can collide with the neutral atmosphere and drive large winds. We talked about the km/s winds that you can get up to, that if it's in track would affect the drag of a low Earth orbiting satellite. And and of course that dual and particle heating heats the atmosphere and causes the thermal expansion, the neutral density increase, and affecting the drag. And then that heat source drives a global pressure gradients and equatorward wind surges and a whole change in the global circulation. And I'll go through some of these things in more detail as from the second half. And that can cause neutral composition changes and positive and negative ionospheric storm effects. And of course you have the dynamo effects going on as well. I'll just maybe mention a little bit about satellite drag before we have a break. Of course, the drag is affected. The direct effect of drag is on the orbit prediction, and but there's an indirect effect of the impacts of the inability to monitor and predict debris trajectories, and so for collision avoidance. And and of course the main drivers are the solar wind and the magnetosphere ionosphere forcing, which is for a geomagnetic storm. And of course you can have the EUV increase as well. Is this a good point? I'll just say a little, just say a few more, as I wanted to get a couple of more slides, but just in one more minute maybe. So the atmospheric...
No problem, Tim. You have 3 minutes.
Okay. So the atmospheric expansion posed two fairly distinct risks in operational spacecraft for orbit prediction. One is the direct effect of the enhanced drag on the spacecraft, changing its orbit, increasing the uncertainty of its position, and reducing the orbit lifetime. And then the indirect effect of the atmospheric expansion on the ability to monitor the trajectory of all the debris that's up there, including objects with high area to mass ratio, and that's for collision avoidance. So the neutral density responds to this thermospheric heating, and an increase in temperature and increase in density, we've sort of considered those fairly synonymously. And then of course, if you have a lot of structure or waves propagating around, then the debris with the high area to mass ratio is the most affected, would affect the collision avoidance. What's the next slide? Yes, maybe I'll just cover this one and then we'll have a break. There's a nice way of thinking about it. This Joe Carell thinks about it in terms of the larger objects, which he calls cars, and then the smaller type objects, which he calls hubcaps, and the shrapnel, which is sort of flecks of paint and things like that. Gives you an idea of the number of those objects. And the cars are easy to track, the large objects are easy to track, but if they do collide, that's the source of most of the debris. The hubcaps, there's not many of the hubcap size, if they collide with a car, that they're not very likely to create, they might damage the satellite, what they call the car, but they might not actually shred them and cause an increase. So this idea of this Kessler syndrome, where we worry about a cascade of objects, we have to be careful about how we use that analogy. So yeah, I'll just hang here and we'll have a break. I'll just check what the next slide was, but I've just got a few more things about why don't we have I'll stop sharing my screen and we'll have a 10-minute break, and then we'll come back a little bit more about satellite drag in a few minutes.
Thank you, Tim. Going really well. So your break for 10 minutes. We resume at 8:30.
That sounds good.
Boulder time. Thank you.
Tim, let me just jump in and ask. I know there's lots of satellites and drag affects them all, but of course, some of us are mostly focused on scientific spacecraft. Do you remember there was one that was lost to drag rather suddenly? Was it? It wasn't Yoko, I don't believe, but it may have been like Astro D, or you may not remember.
Yes, I mean there certainly was a lot. One of the, I think it was one of the space stations. You know what? I think it was one of the Russian. What do they call the Russian space
Oh,
station?
Mir.
I think the Mir came down. I mean, it might have been 10 years ago or something, but I think there was a couple of big storms, and that brought it down quite quickly. And that's rather a large object to be coming into the atmosphere. I think luckily it landed somewhere either in the ocean or in the middle of nowhere. But yes, I mean, of course, that's happening all the time.
Yeah, no. This was I think caused by a flare, and so I would usually taunt I think it was one of the X-ray astronomy satellites, the Japanese X-ray astronomy satellites.
Yeah, that's what I was going to say. I'm trying to sort of
Lika, was it? Because I would taunt them by pointing out how, how their field was being impacted by space weather, by solar flares, because
you know what I do? I talk to the climate scientists about that. I say, hey, you get your handheld prediction. I mean, if the satellites go, your data goes. You have no information.
Yeah, I think this basically it didn't bring it out of orbit immediately, but what it did was deflected it. It changed its orbit significantly enough that they lost tracking on it, and then they didn't get any commands to it for too long. And
wasn't that Adios 2?
What?
Was it Adios 2?
It might be.
Yeah, let me go look. I think it changed its orientation to the point that it couldn't get its panels energized.
Yeah. That was it. That was the one. Okay.
Tim, do you mind if I ask a question while we're on break? No, that's fine. I appreciate the conversation. Can you hear me, Tim?
I can.
Okay. One of the things that I've been looking at lately is actually at Mars, but it's thermal tides and how these might affect orbital maneuvers or landing procedures, things of that nature. And I'm just curious if that's also factored into something like the plot that you showed. I think it was the second to last slide that you had before we went to break.
Say again, thermal what?
Thermal tides, so variations in density, yeah, but usually, at least from what I've seen, organized longitudinally.
Yes, the global models do have sort of the tidal variations in them, at least the physical models. And of course, depending on the orbit, you will see and how it coincides with some of the larger tides. Then I'll show some of the comparisons, along particular orbits. And the main tide, of course, is the big, large diurnal tide, because it's hotter on the day side than the night side, just the in situ driven tide. But the tides propagating up from the lower atmosphere, the biggest effects of those are more sort of between 150 and 100 and 200 kilometers altitude, which is a bit low so it would affect trying to predict re-entry. But the magnitudes of the tides up in the F region, of course they do propagate up, but the in situ diurnal variation, which of course has other harmonics, semi-diurnal and terdiurnal, and so a lot of those tidal variations, yes, I mean, tidal variations, of course, is either from the in situ heating, but people often think of the tidal variations being the ones that are propagating up from below. But it's more the in situ tides which have the bigger impact, the large diurnal variations. And I'll show some sort of a little bit of what they look like. But yes, tidal impacts are definitely important for this orbit prediction. And because, they want to predict out for 3 days. So and trying to get that, predicting what the atmosphere will look like over the next 3 days is tough. I mean, that's one of our challenges. Whether there's a storm or not, even if it's just day-to-day variations.
Sure. Yeah, I guess I didn't really consider the fact that they're likely dampened out. At least the significant portion of those signals are dampened out before they get to that altitude. But I guess now I'm wondering if it could affect communication in a significant way from spacecraft to ground.
Yes, I mean, there's sort of at low latitudes, of course, just waves generally that propagate up from the lower atmosphere can cause a lot of fluctuations and irregularities in the ionosphere that has affected communications. And of course, at low latitudes, they can be quite strong. So not necessarily the tidal effect, but just all of the fluctuating waves that are propagating up. And of course, the F region undulations and that will affect the HF propagation as well. But yes, there's all sorts of, but the tides themselves, not a, I'm trying to sort of put those in, you don't, I mean, of course, the geomagnetic storm response is always the biggest thing. And then we're starting to explore some of the forcing from the lower atmosphere and what happens during a sudden stratospheric warming and things like that.
Sure.
Which effectively is, the sudden stratospheric warming is changing the tidal amplitudes. And so then, yes, actually, now you've made me think. The tides are really driving the electrodynamics, because that's the region where the collisions between the ions and the neutrals are driving in the dynamo region. So then you see the signatures of the tides in the electrodynamics, and then the electrodynamics is then what's driving the plasma. So they do have a bigger effect. And I sort of misspoke a little bit before, but it's coming through the electrodynamics.
Okay, thank you.
So, if the students can turn on their cameras to let me know that they're back, and while you're doing that, Rhonda has a question also.
I had a question during the break. I don't know, do we have time? I wanted to ask something from the first part when you show this Chapman results of density during the solar flares. And as I have seen on this graph, it shows increase of density during the solar flare, but this increase also lasted like half a day or more. So I thought that a solar flare produced sudden ionization, but I see the effect lasts longer. And
yes, that's the extreme ultraviolet part of the flare. So it's not the 1 to 8 angstroms. This is more at the 50 to 100 angstrom. Sorry, not 50 to 100. 50 to 100 nanometer wavelength. So the longer wavelengths, that the extreme ultraviolet as opposed to the X-rays, and they have a lot longer. They have the same. Well, they have a slightly different time history. So it's not in response to the X-rays part of the flare, but you can have the extreme ultraviolet part of in the solar spectrum. We call a flare, and that's synonymous with the X-ray part, but a flare also sometimes has an extreme ultraviolet part of the spectrum that's increasing at the same time. And that's the thing that gets absorbed higher, that has the much longer time scale. The X-ray part doesn't do that. That has a very rapid response and recovery, because it's more of a a chemical equilibrium effect in the D region. So it's a very rapid response.
Okay, thank you for clarification.
I'll just close my door. Should I get going again?
Yes, I think so. So. And I will keep an eye on chat and for hands raised for questions as they come up.
Great. Okay, so I rather like this, this terminology that Joe Correll uses of, the large objects. And of the large objects, not all of those are actually operational satellites. There's a lot of just you know, large rocket bodies and things like that are up there that are just tumbling away in creating collision risks. And if it's an operational satellite, normally they have some sort of way of if there's a if they're told that there's a potential conjunction between one of these large objects, they can move out the way. But if you've got two objects that are not being controlled, then of course they can collide. But luckily they don't collide too often. So, but the hubcaps, those smaller items, there's a lot more of them, and you can track a lot of them now with so I think they track about 20,000 objects at the moment, but a lot of those were caused by just two collisions, and I'll show you what they. But and Joe reckons that it's, you know, that there's this. You don't really know how much of these smaller objects, stuff that's an order of a gram, and that can damage a solar panel, and you know, that can actually disrupt a satellite. They're not going to cause the satellite to break up and shred and create a lot more debris, and that's where he thinks a lot of the we should worry more about this all this small stuff that's up there that is too small to track, at least at the moment. Anyway, it gives you sort of a bit of a picture of and the number of collisions that will actually cause this cascade is quite small. It's only a small part of the hubcaps and these larger objects that are big enough that they will actually cause the whole things to shred.
We have one student question, wanted to know whether those are mathematical estimates of collisions, or we really know those collisions.
I think I mean, there's 20,000 objects that are tracked, and they're predicting the orbits of all those 20,000 objects routinely. and if there's a conjunction that, you know, closer than a certain distance, then that will inform the operational satellites that you've got this conjunction, you might need to do a maneuver. And the International Space Station routinely does maneuvers to avoid some sort of objects, you know, whether it's a large one or these hubcap size objects. So yes, no, they are mathematically predicted, and stuff that isn't tracked, of course, is just you know, just wherever it happens to be, and it can be grouped in altitude and orbit planes and things like that. So some of it is predicted and mathematical, and some of it's not.
Thank you.
And this gives you an idea of the sort of the altitude structure of all of these hubcap sized stuff, and a lot of them there was a collision between an operational Iridium satellite and an old Russian Cosmos satellite that created a bunch of debris. And then there was a deliberate Chinese satellite missile test where they deliberately blew up another satellite, which was very annoying because that created a lot of debris. And so, you know, 50% of the debris of that scale size is due to just these two collisions. So you want to try and minimize those as much as possible. And this just gives you an altitude profile, but I think it gives you the essence of where the information is. I don't think I need to go in. It just gives you a bit more information about the altitude distribution of some of the material that's up there and who it belongs to and how big it is and things like that. But it's not really relevant for the physics, I don't think. So we have models that at the moment, a lot of these orbit predictions are done with empirical models, the UCAR Bowman model. And of course, our physical models are now getting to the point where they can be used to predict satellite orbits. And the bottom left here shows them orbit going through a neutral density distribution from a physical model. And then as you go along the satellite orbit, you can see we can follow the response to some of these geomagnetic storms quite well. And even at the high resolution, the figure in here, you can see you're following the structure and the storm response quite well. So Potentially they have a bit more of a predictive capability as long as we know what the drivers are. So there is a move to try and move from using empirical models for this orbit prediction to physical models. And just give you an idea of some of the things that happen in the physical model. You think that when you have a storm, the density increases at high latitudes, and it would be all very, very, very simple. But I don't know if this is going to work. Yes. Here's just an animation of what neutral density looks like at about 400 kilometers altitude in response to a geomagnetic storm. Here it's sort of quiet, but then the energy suddenly gets injected at high latitudes. But you can see it doesn't stay there. The waves propagate equatorward. And here, at this time in the middle there, you've got the maximum density changes at the equator. And that's because the energy that was dumped in at high latitudes are propagated to the equator. Then you get an interference between those waves. So it's a very dynamic system that you're trying to predict. And if you've got orbits flying through that, you've got to have a very good neutral density model to work out orbit prediction for that type of thing. And if you look at it, these are some of the waves that propagate, and you can see them in observations as well. So that's some of the challenges of trying to model the neutral density well enough that you could predict the orbit flying through through this very complicated structure during a storm. And when you get all these, bumps and wiggles, those objects that have high area to mass ratio, it's not just the orbit average that's important. You need to know if you're flying through a big neutral density bulge, that's going to slow you down. And just for your orbit prediction and collision avoidance, it's a tough job. So, but it's a very important job. I don't think this is just another example of that. So our physical models, I think, are getting much better. And we're getting to the point where I think we will be able to use physical models, and we're actually using even whole atmosphere models to do it. And I was just going, because we're using this for other things as well. So I'll just show a couple of examples of, you can see that this is the comparison. Every orbit, if you imagine an orbit flying through this global distribution, say this is at about 300 kilometers altitude, I think, or 250 kilometers altitude. And there was a satellite that had an accelerometer on it that was flying through this region at about 250 kilometers altitude, called GOCI. And you can compare what you would see if you were flying through the physical model versus what the estimate of the neutral density would be from the accelerometer on board. And there's two lines on that top trace there. One's the blue line, which is the density prediction. This is neutral density. This is the density prediction from the model versus the black line, which is the density prediction from the GOCI satellite. You can see, you can follow, it's flying through this whole diurnal variation. So there's a dayside peak and a minimum on the night side. And then there's lots of bumps and wiggles, of course, from forcing from the lower atmosphere. And you can see, the quiet day before the storm, you're actually following the variations along the orbit incredibly well. And then even when you go through the storm, if you look at the individual traces, each of these is one orbit. There's two peaks and two troughs of every orbit as it flies through the day side, dawn and dusk, and then the polar regions are the minimums in this case. Then you get the storm. The orbit average is the continuous line through it. But you can see even during the storm, you're still following some of that dynamic structure during the storm. And then as you go into the recovery. So for a modest storm, you can actually model with a physical model that neutral density response quite well. And we hope that we'll be able to improve the orbit prediction and collision avoidance and things like that with these physical models. And of course, the bigger the storm is, the bigger response. So this would be what you might see at 500 kilometers from the big storm in 2015. You can see you've got about a factor of 300% increase, a factor of 3 change in neutral density. And for this storm, this major storm in November 2003, there was actually about a 5 times increase in the neutral density for this big storm at 400 kilometers altitude. So they're big effects. So compare that with that 50% increase during the solar flare, for instance. And I think that was, yeah, so this was just, I won't go through all of these again, just for the interest of time, but I will try to, I'll go in a little bit more about some of the ionospheric effects. Are there any other questions in the chat on satellite drag?
No, it doesn't look like it.
Okay, good. Okay, so I want to go on now to talk a little bit about how the CME or the geomagnetic storm affects the ionosphere. That was sort of how it's affecting the neutral atmosphere and the satellite drag. And we've known for a long time that you get depletions in the ionosphere during a geomagnetic storm. And you see there's a good example here that's from a long time ago. This was a storm in 1973. And you can see this is the diurnal variation of the, this Nmax is the peak F region plasma density. So it's a ground-based ionosonde, an HF instrument that's measuring the peak F region plasma density. And this is the normal diurnal variation. You can see the median is the normal diurnal variation. And when this storm occurred, then it completely wiped out the F region ionosphere. And you can imagine if you're trying to communicate with HF and your F region disappears, you'll no longer be able to reflect your wave off the F region. And so you would lose that signal. You do also get some positive phases seen in this image. And what we want to do is try and understand what the cause of these negative and positive changes are that will be affecting HF and communications, etc. And we now understand that the reason for this negative phase is in fact a lot of the changes in the neutral composition. And on the left-hand side, you can see that the bigger the storm, then this composition is measured by the ratio between the N2 and the atomic oxygen neutral atmosphere. The N2, if you have more molecular nitrogen in the F region, the loss rate for the plasma is much more rapid than if you have oxygen. So if you have a storm that increases the N2, then you will deplete the plasma. And this gives you an idea of what that ratio, how much the N2 increases versus the oxygen. The stronger the storm, you get the top figure on the right shows the bigger the storm, the bigger this into the O change, into over O change. You have a seasonal effect, so you have a bigger effect in in the middle it's actually winter, but you have a local time variation, so it's a bigger effect between 0 and 6 UT versus at 12 and 18 local time. And then there's a summer-winter difference. So in summer, it will penetrate to lower latitudes, whereas in winter, it might be higher, but more confined to high latitudes. So we want to try and understand what causes that. So, and again, we need to understand the physics of the response so that we can give a little bit of a prediction. We don't just want to be able to specify what this is.
Tim, I hit the wrong button and I muted you. Tim? Oh no.
Yeah. Can you hear me now?
I'm sorry. Yes.
Okay. How long was I muted?
Just for about 15 seconds.
Okay.
I meant to unmute myself. So there's there are a couple of questions in chat on this.
Yeah.
So one is just can you just go over the idea that heating inflates the neutral density briefly? I think that's a counterintuitive concept.
Okay. The question was referring to the plasma, the positive phase in the plasma density.
Yeah. So the neutral density. The question is, the neutral density increase is due to heating and inflation? Question mark.
Well, yes, the neutral density is because of the heating and the inflation of the atmosphere, but the ratio between the N2 and the O that's affecting the ionosphere is something different, and that's the global circulation changes that are affecting the O to N2 ratio. It's the difference between what you see on a fixed height versus on a fixed pressure level. Pressure level in the atmosphere is more important because that's the level of the ionization rate. If the atmosphere expands, but a production source from a solar photon would get to the same pressure level, which would be at a different height. So the pressure level is important for the ionization source. So the loss rate that comes from the N2 over O is more dependent on the pressure level. And that doesn't change with a thermal expansion. It has to be a circulation change, and actually of transporting the N2 from the lower altitudes up through the pressure levels. I'm not sure if that sort of, I'll talk more a little bit about this as I go through. But yeah, but the neutral density changes and the composition changes that are affecting are slightly different physical processes.
Okay. And so there is a question just about that and how the storm affects that. And I don't know if you want to cover that now or later. How does the storm affect the N2 or O separately?
Okay, let me go a couple of slides on because I've got a little bit more information about that that might help explain it. And if there's still it's still not clear, we'll go back to that question. So this is when you saw that when that neutral density response, the energy initially goes in at high latitudes, and so the energy goes in this region here. That causes a local heating and expansion, but then that starts to drive a circulation, that a divergent wind out of that source region. And if you have a divergent wind, then you have a vertical wind transporting the stuff beneath you up to that region. And so this figure on the that shows that blue patch, that's a region where the N2 has been brought up from the lower atmosphere to that level where the F region will be depleted. So it appears as an oxygen depletion, and it's actually where the N2 has been transported up and has pushed the oxygen, the neutral oxygen, out of the way. And so that enhancement of the N2 here, which is seen in the bottom two figures in a physical model, is seen as the increase in the mean mass. If you have more N2, which has got a mass of 28 versus the oxygen, which has a mass of 16, then the mean molecular mass increases. And the region where you see that increase in the N2, you can see the depletion in the plasma density. But it's not the thermal. You need the thermal expansion locally, but then you have you have a circulation that is then responding to that transports the N2 to the higher altitudes, where you then see the depletions in the plasma. Does that explain a little bit better? That person that asked that question, just give a thumbs up or thumbs down. If it's a thumbs down, then I'll come back to it later. If it's a thumbs up, then did we get a thumbs up on that, or neither? I'm looking
for Deb, who asked the question. I don't. Okay. Yes, Deb has a thumbs up. That's fine. Oh, I did it again. There we go. Sorry.
You're sending a subliminal message to me.
No.
Okay. So this understanding about how this negative phase, the seasonal variation of this negative phase, has been understood it's been observed for a long time. It hasn't been understood for a long time. But you have a large. How am I doing? I've got about half an hour, haven't I? So these were some excellent analysis. This was an ionosonde in Argentine Islands. It's a southern hemisphere mid-latitude station, and what's being plotted is the the peak plasma density, if you imagine that F region peak, and what it is on a storm day compared with a quiet day, that ratio of the N on the storm day, the plasma density on the F region plasma on a storm day compared with a quiet day, that ratio, it happens to be just the natural log. But you can see that, so if you're below the 0 line, then if it's above the 0 line, then it's painted black. So that would be a positive phase. And these are diurnal variations as a function of season. So it goes from January, February, March through to December. So you can see that in the Argentinian islands in December, which of course will be summer, it tends to be on most local times, it's a negative phase. It's below the 0 line. You can see the 0 line because you can see the difference between the black bit and the clear bit. So if it's above the 0 line, it'll be black. So you can see most of it in the summer here in mid-latitudes in the Southern Hemisphere station, which would be summer, is negative. Compared with in winter, it tends to be a lot more positive phase, an increase in the plasma density. And of course, you can see this very strong diurnal variation. And we now think we understand both that seasonal variation in where you get the positive and negative phases and this diurnal variation. And it's because of this, as I was talking about, if you have the heat source locally at high latitudes, it develops that circulation and it causes that upwelling. And this is an evolution of that mean mass. So if it's an increase in the mean mass, then it's an increase in the N2 and the O2, in the heavier species, heavier neutral species. There's 3 main neutral species in the thermosphere. There's the atomic oxygen, N2 and O2. The N2 and the O2 tend to settle out to the lower altitudes and the oxygen tends to settle out above. So when you have one of these upwelling events, it's carrying the N2 rich gas to higher altitudes. And so you see these increases, which are the things that cause the negative phase. But as you go through this storm sequence, this is like over 48 hours, 2 days, you see that this bulge expands equatorward and expands equatorward because at solstice, there's a circulation from the summer to the winter hemisphere. So that's transporting any composition change that you get. The global circulation is transporting that equatorward, whereas in winter, the winds are coming towards the polar region, so it's confining the composition changes to the high latitudes, whereas in summer, it's trying to spread them out. So that explains that summer-winter difference. And this blob, if you look at sort of as every 6 hours, you can see that the thing is actually moving poleward and equatorward in a diurnal way. And that's just the diurnal variation. On the day side, the winds are poleward. On the night side, the winds are equatorward. And it's just this bulge of composition responding to the diurnal variations of the winds. So we think we understand that seasonal variation and that diurnal variation because we were able to model them in a physical model. And of course, and you can model out those composition changes quite well, as long as you get the right energy input that's driving the global circulation, and you can monitor whether you're getting the right energy input to see whether you're following the neutral density changes. So if you can follow the neutral density changes at say 300, in this case it's 450 kilometers altitude, you know you've got roughly the right amount of energy coming into the system. You know it's going in at high latitudes. So then you can start to predict what the global circulation would be and also what those composition changes will be. This transport of the N2 from the lower altitudes up through the pressure levels and then trying to transport it equatorward in the summer hemisphere, and it will get constrained in the winter hemisphere. So, and then once you get, if you're in a region where you have that big upwelling, which in these comparisons were between the O to N2 from observations from the Gooby satellite versus WAM, which one's which? They look so similar that it's hard to tell which one's which. It doesn't actually matter. But if you're in this is the observations from Gooby. If you're in a region where the blue is increased, which means that the O to N2 ratio is decreased, means you've got more N2, got more loss rate, and that if you're in that region, that's where you'd get your depletions. You'd get the upwelling causes the increase in the N2, faster loss rates, and the negative phase. And in principle, if you have a downwelling, you could have a decrease in N2 and a slower loss rates, but that turns out to be not the dominant driver of the positive phase, but it's certainly a physical process that's going on. Were there any other questions? That was what I was going to talk about with the negative phase, and then I'll go into what drives these positive phase increases. Was there any other questions on the negative phase, or should I keep going?
It doesn't appear to be any questions right now.
Good, great. Okay, so the negative phases certainly affect HF. They don't have a big impact on the GNSS, positioning, navigation, because it tends to be larger scale, those negative phases. But the positive phases, they tend to have a lot more structure, and it's because there's another physical process that's also going on during a geomagnetic storm. And you can have quite a modest, this is a geomagnetic storm that occurred in February 2014. The KP only got up to 6 here, and only a very short duration. But the timing of it was such that there was large plasma density increases over the US, and we had an operational product that was monitoring the plasma density over the continental US. And surprisingly, we saw this very large increases in the plasma density. And it was a really modest storm. And it just so happened that the storm hit when this sector was in the noon to dusk sector, this 12 to 18 local time sector. And at the same time, there's the civil aviation, they use they call it the wide area augmentation system. It's a navigation system that's used for navigation on domestic routes and over the US, and that it improves their navigation accuracy, their GNSS navigation accuracy, because they give corrections. And during this period, there was so much disturbance in the ionosphere that they could no longer guarantee that the corrections that they were sending to the airlines was correct. So they had to say that the WASP system was out of order. And this happens sometimes on big storms, but this was a very minor storm to have this effect happening. And it was just because of the timing of the event. And you also get these, as well as getting these large increases in plasma density, and clearly the structure associated with that caused the WASP system. The WASP system is a bunch of ground-based GPS observations, GNSS observations that try to map the ionosphere. And if they think they can map the ionosphere well enough, then they can put out corrections. But there was so much structure and gradients, they gave up and they said, nope, can't do it. Don't use these corrections. So they have to start, either assuming that the accuracy of the GNSS was much poorer, or they had to use some other navigation system. Now the driver for this, you can see that these are in the bottom right. You're still able to see my arrow move, is that correct?
Yes.
Good. You can see this region between at mid-latitudes, between noon and dusk, you can see the normal plasma convection at high latitudes. It's anti-sunward over the pole, and then sunward in the dusk sector, and the sunward in the dawn sector. And you can imagine that this is superimposed, this pattern of convection is, you imagine that's fixed, and as the Earth is rotating underneath, that convection pattern is sort of in that fixed frame as a function of local time. And so if you're on a location on the surface of the Earth, you would actually be moving under that convection. And if that convection is expanded over the continental US, then you can see that that is sort of bringing the plasma sunward. These are plasma convection arrows. So whereas normally at mid-latitudes, the convection might be weak, the plasma will just be moving through local time, and then it would be going through the afternoon, and it would gradually be decaying away, and your F region plasma would be decaying away. But now you're picking up that plasma with this convection, and you're actually carrying it in the opposite direction from the rotation of the Earth. So a parcel of that plasma is virtually stagnating in local time. So the plasma staying there, the atmosphere that's surrounding it is continuing to, if it's in the sunlight, is continuing to be ionized. So the plasma density in that region just keeps going up and up and up because it keeps stagnating. It creates an ion, the electric field will pick up that ion and will move it towards the sun side. And so it will just keep building up the plasma on the day side. And if there's a slight, you can see as you go towards midday, it actually starts to go poleward. And given the fact that the magnetic field is tilted, that E cross B drift, this is the plasma drift, is actually taking it to higher altitudes as well. So it's not only stagnating and increasing density, it's also taking it out of the atmosphere where the loss rates are much less because it's not it's not experiencing as much background N2. So all of those effects going on, the plasma convection and the change in altitude of the plasma gives you these huge increase just in this local time sector. So that's the reason why you get these large negative phases. Any questions on that before I go on?
Tim, is there also any kind of relationship between the weakness of the geomagnetic field in that time sector, or is that just not a player?
Yes, obviously the magnitude of the drift will depend on the magnitude of the B locally, but I don't believe it, unless you're in the South Atlantic anomaly, and these things aren't happening in the South Atlantic anomaly. That would be more of a low latitude effect. So I think the magnitude of the B doesn't have a big impact, I would say. The magnitude of the plasma drift can go from, nothing to 2 kilometers per second. It's such a huge change in the plasma drift that a modulation of B of 20 or 30% or something doesn't have a big impact, I don't think, not in terms of the understanding the physics of it.
Thanks. Okay.
It would certainly modulate it, obviously, because it's an E cross B over B squared effect.
Thank you.
So we have a physical model now that we think can produce these mid-latitude effects and these tongues of ionization that you get that create a lot of that structure. And these are and of course, if you put in the right plasma convection, then this is the change in the it's actually the total electron content in the buildup of plasma. This is over, you can see over Florida, over the middle of the United States, and then this tongue of ionization. And you can see the observations show in similar locations that's where it actually happens. So we're able to model it now and hopefully predict it. And if we know what the solar wind is going to do and predict what the plasma convection might be doing over the next few hours, then we might be able to predict these wipeouts of the wide area augmentation system and the impacts on communications and navigation, GNSS navigation and communications. You also get these tongues of ionization. The buildup of plasma that we're talking about is occurring down, say, at the mid-latitudes, and then the plasma convection then carries some of that plasma poleward. And you can get all these tongues of ionizations, and if you look at the edges of some of these tongues of ionization, you can have huge gradients. So it's just like having a blob of plasma, and the radio wave passing near that steep gradient will just diffract the signal, and you'll have fades, you'll have scintillation and amplitude fades in that signal due to some of these steep gradients on these what we call the storm enhanced density features. So on the left might be a quiet day, and on the storm day, you got that buildup of plasma at sort of mid to low latitudes, and then these tongues of ionization during quite a big storm. What's this one? This one happened to be in March 2001. So we think we understand the physical processes now, and hopefully we can forecast it. And we can say, yes, although we can't resolve these sort of gradients, we can say, yes, we get these SED feet. There's going to be an SED feature over this region. And if you're taking off from DC or something and you're going to be flying through some of these steep gradients, and you might see communications problems if you're using satellite communication. We can't predict this we can't model these gradients, but if you know where they are, you know that there's probably going to be some of these gradients around, and it gives them a heads up. As you get down towards, this is rather a lot of information here. Sorry about that. But the large increases that we were just talking about are these features that were seen from a satellite at mid latitudes. That's these features here that on a quiet day, this might be what you would see from the satellite. In this is that dusk sector, and it can increase in this region. You can see that there's sort of rather two distinct regions. There's this sort of mid-latitude region, which was the effect we were just talking about. But there's also that secondary peak here, which is more down at low latitudes. And there, normally at low latitudes, you have the global structure of the plasma. The really obvious structure is the equatorial ionization anomalies. Those are you have worked in the ionosphere, and so you get a peak either side of the magnetic equator, and that occurs pretty much all the time, just from the quiet time diurnal variations of the electric fields, just from the dynamo effects. When you have a big storm and that penetration electric field at mid latitudes, we saw what happened, but at low latitudes it causes those anomaly peaks to expand to higher latitudes, and you get these large depletion at the magnetic equator. So this effect is going on at the same time as the mid-latitude build-up effect, that stagnation effect, that what we call the Helios effect. And sometimes if you had a really big storm, those two things would be pretty indistinguishable, and they would sort of and this is almost merging here. And so you would deplete plasma at high latitudes, because you have erosion of plasma and then it gets lost out into space, and you would deplete plasma at low latitudes because of these electric fields and movement of the anomaly peak. So you look at the plasma sphere from space, you see a large erosion of the plasma during these events. I'm afraid I haven't sort of devoted a lot of time to the electrodynamic part of this presentation, but I just wanted to sort of give you an idea that these things are going on. And there's a storm time dynamo as well. But again, I think I'll spend the last 10 minutes just going on to the next thing. Maybe we can talk about this a little bit more tomorrow, but the storm time disturbance dynamo is just another source of these electric fields, which are creating the redistribution of plasma, both mainly at low latitudes, these equatorial ionization anomaly effects. So this is just sort of summarizing some of those ionospheric storm effects. You can have that buildup of plasma at mid latitudes with storage on the top side due to that those electric field effects, and also because it might have equator with neutral winds pushing the plasma up as well. You have all those storm enhanced density features, like here, from once you have that buildup of plasma, that you have steep gradients on the edges of those. We talked about the negative phases from the composition change, wiping out the F region. And we just briefly mentioned here the poleward movement of these equatorial ionization anomalies. And all these things going on makes it look like the plasma is being completely eroded. So, within the region where you have the increases, you have a lot of structure, but globally, it looks like we're eroding a lot of the plasma. So there's some of the physical processes that are going on that are a lot of the causes of the space weather at mid-latitudes. So I'll just pause for a second just to see if there's any questions on some of those before I just talk a little bit about the waves propagating from the lower atmosphere just in the last 5 or 10 minutes. Were there any other questions on some of these physical processes?
It does not appear so.
Okay, I will go on to.
Oh, there is. Yes, there is one. So,
Yeah.
So Krishna is asking what the typical timescales for some of these processes are.
Good question. Yeah, the this buildup of plasma, that bulge that we saw, that this Minucci figure sort of is this sort of mid-latitude increase, that can build up over a period of sort of 2 or 3 hours. The production source is solar EUV ionization, and so it just sort of stagnates in that region, and so it takes 1, 2, 3 hours to gradually build up. So that's the sort of time scale. And this transport over the pole, again, the sort of plasma transport might be a kilometer per second, might be 5 kilometers per second. So it gives you an idea how long it would take for that plasma then to be transported over the pole. And so that can happen quite quickly once you have a buildup of plasma, you know, but you've got to have the buildup of plasma to start with that creates the source. And then you can propagate that and create some of these steep gradients very rapidly in a matter of, you know, minutes to hours. The negative phase of the ionospheric storm is a gradual. It's a gradual buildup of the. It can take a few hours for the neutral composition to really respond and create. It's the global circulation, and so that can take a few hours to kick in, but it can last for a day or two as well, because all of that transport of the neutral composition has got to try and diffuse back or flow back to where it was before, back to the equilibrium case. So it can take, you know, a few hours to half a day to respond, but then it can take a couple of days to recover. The equatorial ionization anomaly, I mean, that in an hour you could go from the quiet to the disturbed case, so about an hour. So although the plasma transport response is very rapid, it takes time for the actual plasma buildup to occur and the transport to occur as a result of that. The plasma density, the plasma convection changes can happen in seconds or minutes, but the actual plasma density changes take longer. Any other questions on that?
No.
Okay, so I'll just talk for 5 more minutes just about some of the waves propagating in the lower atmosphere, and I'll put some of these in the talk tomorrow as well, because we're not going to be able to get through them. But I just wanted to give you a flavor that not all space weather effects are caused by the solar variability. They're all caused by the solar energy coming in, but it's just like in tropospheric weather forecasting is that the day-to-day changes in weather is not due to a change in the solar output. Obviously it does change, but that's changing by 1 part in 1,000 over long time periods. The day-to-day changes is because it's chaotic. It's deterministic but chaotic. And so you have all those waves propagating up from the lower atmosphere that doesn't need a geomagnetic storm. You don't need changes in the solar output. It's due to the energy going into the troposphere and then the waves propagating up from the lower atmosphere. That's all the stochastic variations. So if you look at 250 kilometers, if you didn't have that source in the lower atmosphere, this would be a very smooth vertical wind pattern. But as it is, you've got all of this structure, all of these bumps and wiggles. This is plus or minus 10 meter per second vertical wind. And you get you know, during a quiet time, this would be less than 1 meter per second, unless you had all these waves coming up from beneath. And we believe that all of these fluctuations are one of the causes to trigger ionospheric irregularities at low latitudes. There's irregularities form at low latitudes due to things like the Rayleigh-Taylor instability and things like that, which I can't go into the details. But the driver of the, you know, the trigger for those irregularities can be all these waves that are propagating up from the lower atmosphere. So they potentially are, and of course you can have ionospheric irregularities on any day. They're nothing to do with geomagnetic activity. So we might have a way with these whole atmosphere models of predicting where you might have a strong wave source, or where the winds might be such that it's inducive to the creation of ionospheric irregularities. And that's just another image of that, but it's more or less the same in temperature. And we've known for a long time that the structure in the lower atmosphere is driving structure in the ionosphere, but we're now being able to model it and potentially predict it. And I'll probably just do 2 more slides or so. But Tom Immel did an amazing study where he looked at, he saw a strong longitude dependence. You remember we were talking about those equatorial ionization anomaly peaks? These are 2 peaks either side of the magnetic equator. And he noticed that there was a strong longitude structure in the magnitude of those peaks. So you can see that there's four peaks, and the southern hemisphere is just a mirror image. It's a bit of a contrived image, but you can see that there's 4 peaks. And we believe that's due to a tide that's propagating up from the troposphere called the diurnal eastward propagating wave number 3. The tidal nomenclature is a bit of a mouthful, but it just means that, well, I'll describe a little bit, but we believe that that tide propagates up to the dynamo region and to about 150 kilometers altitude and is driving the electrodynamics. The electrodynamics is then moving the F region plasma and creating this longitude structure. And the source of it, we believe, just in the last minute, is tropical convection down at low down in the troposphere. And tropical convection, this is just sort of indicated by lightning strike frequency, and it tends to be maximized over land masses. So you can see you've got a strong longitude structure, and if there's sort of a bit of one here, but they're actually about 90 degrees apart, these central points. And if you have if you had another peak out here, you would actually have 4 peaks. And if you have 4 peaks in longitude structure that then is modulated by a diurnal variation, then mathematically you can actually create this diurnal is the frequency here. The 3 is 3 peaks, and the negative is the eastward propagating. So it produces a structure that has 3 peaks that is moving eastward through one cycle every 24 hours, which is why you end up seeing the 4 peaks here, because over a 24-hour period you see 4 peaks. And I think I might be, yes, I'll talk more about the other sources. So this is a very strong source creating the longitude structure in the ionosphere, as well as all of that wave source. I'll just flip to the end, and I'll try and just cover these last 3 or 4 slides tomorrow. This is another indication of those waves that propagate up from the lower atmosphere, drive undulations in the F region, and you can see those actually in the total electron content, and creating all these undulations. But I'll try and review some of this tomorrow and some of this. So just to summarize, the thermospheric ionosphere is the endpoint of much of the solar and magnetospheric forcing of space weather. actually the host of many of the impacts on operational systems like HF propagation, satellite drag, satellite communication, navigation. But just wanted to let people know that space weather can also be driven by the chaotic lower atmosphere, which has sort of changed our paradigm a little bit for space weather. So that's my pitch. I think we're out of time, aren't we, Nick?
Yes, it is time for any a break in, but and any questions first. And
I put my email here, so
Wonderful.
thank you. I'll put my email here, so yeah, make a note of that. Any of the students that want to send email questions over the next few days, I'm happy to, try to respond as best I can. And I think we've got a thing at 12 noon to noon tomorrow. Is it noon today? I think, isn't it, Nick?
There's office hours noon today and noon tomorrow. So yes.
But I can hang around now as well for if people have questions. But hope that's giving you a bit of a flavour what's happening in the upper atmosphere and space weather.
So let's thank Tim for his very nice talk. Yes. Okay. Great. And we will go for let's go for a 10-minute break, which puts us back at let's come back at 11:30 or at half past the hour. If you've got any questions for Tim, this is a good time to raise them. He can also save them for office hours later. And just as a heads up, the model you'll be exploring, the model results you'll be exploring were generated by CTIPI. And those runs, I think, date back to an activity that you put together some time ago, Tim. So we will be using those run sequences as to explore the ionosphere structure and some of the variations that we talked about. So we'll have an opportunity to ask more questions about that tomorrow.
That's right. At the time, we weren't able to get that positive phase very well, but all that negative phase and that global circulation and composition, that's the sort of thing that's targeting in that class.
Great. Questions for Tim? All right, well, let's take a break. Let's be back at half past, and we'll start up again then.
Kendra, can you hear me?
Yes.
Are we planning to meet today?
Afterwards?
Yeah, this is with Hannah.
With Hannah?
Oh, this is Wednesday, right? Our usual whatever.
No, remember we canceled those
Canceled.
for
Okay.
weeks?
Okay, that's still on my, okay.
Yeah, yeah. No, we're on break right now since we're doing all of this.
Okay, thank you.
Was there anything you needed to talk about? Because you can email it to me.
No, I just wanted to make sure.
Sounds good.
Hi, Janet. Hi, Janet.
Hi, Tim. How are you?
Good. How are you?
I'm doing good.
Good. Good. Are you up next? Are you?
I am, yeah.
Good luck.
It looks like you guys are all still working from home.
Yeah, that's right. Yep. Okay.
That's nothing new for me.
Oh, really? Oh, okay.
Yeah.
Yeah. No, I got used to it. It's not too bad actually.
It's kind of nice.
Yeah.
Actually, right before this started, I was thinking that I was getting tired of working at home all the time and I was gonna rent an office one day a week.
Oh, really? Yeah.
Yeah, and then all this happened, so I'm
Right.
just at home.
We're all in the same boat now.
Yeah.
Yeah, I don't find it too bad actually. And you know, we've got our family unit where we can socialize.
Yeah.
Two granddaughters and my son, and so we have our unit that we can communicate with.
Are they all here in Boulder?
Yeah, they live around the corner. Yeah, my son and his wife and the two grandkids live around the corner. So we actually, my Lynette and I sort of look after the two grandkids quite often because they're both still working. You know, they're obviously working, and so they're struggling to manage it. So we take care of the kids quite a bit.
How old are the grandkids?
That's really nice, Tim. My dad, who's 93, I'd like to be able to get to him a little bit more often, but it's a 12-hour drive to get to Missouri, and getting on an airplane is not something that I relish.
Yeah.
So, yeah.
Hi, excuse me. This is Brett from Multimedia. Janet, if you're up next, could you share your screen for us, please? So we can discuss it and make sure that it works.
Let me get this up.
All right.
Is that working?
I can see it. If you'd like to go to your opening slide.
I will do that.
All right.
Yeah,
that looks great.
Okay.
All right. Thanks very much. Yeah, if you want to keep your screen shared, that would be wonderful. Okay, thank you.
Yep, ready to go.
Great. Good luck, Janet.
Yeah, do you have another talk?
Yeah, I've got to talk tomorrow on the ionosphere. Well, on the thermosphere and ionosphere, just more about the physics of the thermosphere and ionosphere. Today's was just on space weather, but tomorrow's will be a bit more of the background. They should have been in the other order really, but it doesn't matter.
Yeah.
Yeah.
So did you talk about satellite drag at all? Because I put that in mine.
Yes, I did have a bit of a section on satellite drag today. Yes.
Okay.
Yeah.
Well,
But
maybe.
it doesn't hurt to duplicate or add to. I'm sure we have different perspectives on things anyway.
Okay.
Yeah, I'll try and listen in.
So the students can turn on their screens to let us know you're back. And Janet, I'm sorry, I interrupted you. Did you have something else?
No, I was just chatting with Tim.
Yes, right.
How's everything going so far?
Everything has been going pretty well, all things considered. I think we'll find out from the students when they give us their evaluations later on in the week. But
I am really impressed with the quick move to online. I guess I didn't go to the CDAR meeting, but I called in for the CDAR meeting, and I was impressed at how well it went. And there's actually some really nice parts of having stuff online, because I would not have gone to the CDAR meeting at all. So I'm finding I can attend more meetings, which is kind of nice.
yes, I have. I think there's some downsides, but also some upsides to this mode. So that.
Yeah, you miss the personal interaction, but you have the opportunity to learn a lot more, and for students, that seems really good.
All right, I think we'll get started. So,
Okay.
If Janet, could you give yourself a little introduction to yourself, just as you begin?
Yeah, I do have one here, but so do you see my whole thing? What are you seeing now?
We see your whole screen.
Okay, so I need to do this, but then I can't see the chat over here.
I will keep an eye on the chat and any questions that come up. So I will let you know if there's questions.
Okay, let me just try and there, that's better.
Excellent, thank you.
Okay, so I actually thought I would start with a little bio about myself, because there's really 3 different sectors where you can get jobs when you're done with your PhD, and I've done all of them. So I'm happy to answer any questions about that. And I'm assuming a lot of you are probably thinking about what you're going to do after you get your PhD. So I got my PhD at UCLA with my advisor, Margaret Kivelson. And if you don't know Margie, she literally wrote the book on space physics, probably that a lot of you guys are using in your classes. Margie's a pretty amazing role model. I think she is 92 now, still doing space physics. I think she even still has students. So if we ever get back to in-person meetings, I definitely recommend taking time to introduce yourself to her. She's always happy to talk with students. After that, I did a 1-year postdoc at NOAA through the National Resource Council, which unfortunately, they're not doing that anymore, but it was a really good introduction to what government service is like. After that, I did a 1-year postdoc at CU with Dan Baker. And then I went back to government service because I actually really enjoyed that. And I was at NOAA for 9 years, both at Sweep C, which I think you guys are all familiar with, and the data center, which has had 2 names. It was NGDC, now NCEI, where I was responsible for monitoring and planning for the GOES and POES particle instruments and making sure the data was all good and developing space weather products based on that and working with customers. I actually left NOAA after 9 years, and I left space physics completely for a short time. And I worked at a nonprofit group where I was using machine learning to try and figure out the best people to target for membership, and also teaching political scientists about statistics and uncertainty when they were doing their testing. So even if you're not quite sure if you want to continue after this, your degree really does have value outside of space physics. And then I ended up coming back and I started my own company. It's called Space Hazards Applications, and the Small Business Administration calls a small business any that has less than 500 employees. Right now it's myself, 2 part-time employees, and a number of contractors. So I'm kind of a micro business, I guess. But hopefully that will grow. And my goal now is to try and develop products for satellite companies to know if space weather has impacted their satellite. And I can't. So I just have a quick question for you guys, and it's what type of career are you considering? And I can't see the chat to know what's coming through. So maybe Nick, you can tell us.
Will do. So in chat, or is there any particular, which particular area are you most interested in? Oh boy, it's scrolling by fast.
Yeah, I guess we don't need exact numbers, but I was just curious, like.
So it does appear to be, so there's lots of slashes and ors. So academic or government or industry, academia. So there's certainly a lot of academic, but there's also a variety of government welfare. Okay, I don't know if that's commentary, but so, and there's also so there's lots of academic, but there's also plenty of slashes and other and the other 2 sectors too.
Okay. I kind of figured it would be mostly academic, but I thought I'd take just a minute to talk about commercial providers and what we do. Because when I graduated with my PhD, there was only really a handful of people that were actually doing this. I'm now part of the executive committee for the American Commercial Space Weather Association, or ACSWA, and there's now 16 different groups that are doing space weather research. And it's a whole number of things that they're doing. So there's basic research that you would do at a university. They're doing modeling, they're developing applications for customers, and there's a lot of instrumentation work. So people building small satellites, radiation monitors, and also magnetometers. And I just wanted to talk a little bit about what I find the best about being a commercial service provider. And I have this quote from my 4-year-old niece who I used to babysit. And when I told her not to do something one time, she said to me, very loudly, "I want to do what I want to do when I want to do it." And I laughed when she said that and said, yeah, me too. But now that's actually what I do. So the best thing now is I have ultimate flexibility. I choose what I want to work on. And there's actually maybe even more funding options right now for small businesses, because I can apply to the same NASA research grants that you apply to at an academic institution, but there's also small business opportunities. There's always something new to learn and a huge amount of variety. And the challenges are that right now I'm basically a soft money person, so it's not highly secure. If you really want to start your own business, that's going to require a lot of self-motivation and a willingness to learn lots of new things. I do finances, I do IT, I do contracts, I do software, and I do science. But probably when you graduate, you're not likely going to start your own company, but it's worth talking to some of these groups because I have a huge amount of flexibility in hiring. So if you find yourself in a situation where you're dealing with other life issues and maybe can't work full-time or can't move to a job opportunity, commercial providers can do a lot of temporary or part-time funding. So that's just something to think about. All right, so the outline of my talk is I'm going to start by talking about space weather impacts to satellites, and specifically anomalies caused by particle radiation, because that's really my main focus area of research. I'll talk a little bit about orbital drag. I think Tim just said he also covered that, but maybe we'll have a little bit of difference. Somewhere in there, I think we'll have a short break. And then we'll talk about impacts to power grids. Okay, so the issue, just really quick, the broad picture is that space weather can lead to an intensification of the particle radiation environment, which in turn can cause any one of these 4 types of issues: surface charging, internal charging, single event effects, and total dose effects. And operating a satellite, it's not quite like driving a car. If something goes wrong, there's not a lot of information to try and figure out what the problem is. And there's a huge number of things that can happen, not even related to space weather, like thermal problems or mechanical problems. But you do want to be able to figure out if there's an issue, if it's caused by space weather, because first it can help you figure out what your response is. If you know the radiation environment is really intense, you might want to wait until things quiet down before sending commands and trying to mess with your satellite. If you know it's space weather, then you actually have some hope of being able to predict when it might happen again. And ultimately, whatever you learn, you would hope would feed back into improving future designs so you don't have that vulnerability in the future. So getting into a little more detail about these impacts, surface charging is when the charged particles collect just on the surface of the satellite, causing high voltages. And those high voltages by themselves are not a problem, but typically you're going to get differential charging, which then can cause a damaging arc or electrostatic discharge. Mostly this happens on solar panels, which is going to cut the lifetime of your satellite. It can also make an electromagnetic pulse that can then couple into the electronics and put your satellite in some really wacky state. Internal charging is very similar, but this is when the high energy electrons actually can just pass right through the external shielding and build up in dielectric materials in the satellite, like circuit boards or cable insulators. Sometimes people put metal spot shields on components that aren't completely rad hard, and the electrons can accumulate on those spot shields. And then at some point, it's kind of just like shuffling your feet on the carpet, and then you get a big zap. At some point, there's a breakdown, and you get an electrostatic discharge, which can completely damage your components or just, again, make up a pulse that can put your satellite into some weird state. And then single event upsets, these are caused by really heavy energetic ions, which you can't really keep out of the satellite. And if they pass through the sensitive region of your components, they can leave an ionizing track, which then flips a bit or completely destroys the component. So either it will make the satellite inoperable or require some kind of ground intervention to fix the problem. And then total dose events, this is just the slow degradation of all the components just due to this constant bombardment by radiation. And if you get a sudden increase, that can lead to a sudden drop in the lifetime of your satellite. So the challenge for space weather is that each one of these problems are caused by different particle components, all controlled by different physics. So surface charging is related to the EV to tens of keV particles, usually associated with substorms, getting injected through substorms during moderate KP activity, and usually you see anomalies related to that over on the dusk side of the magnetosphere. Internal charging is caused by the higher energy electrons, so 100 keV on up, generally associated with storms, and they peak usually around L=4, but extend all the way out to geosynchronous. And then single event upsets, these are mostly associated with solar proton events. And I think you've been talking about this throughout the week, where solar flares, you have a solar flare and then a coronal mass ejection. And as it pushes through the heliosphere, the shock in front will accelerate those protons and they will impact Earth. And then total ionizing dose, that's all of the above. So if you want to predict whether or not your satellite's going to have a problem or try and do any anomaly attribution and figure out what went wrong, you need models and measurements of magnetospheric particles from EV all the way up to MEV, and from 400 kilometers out to 6.6 Earth radii, and models and measurements of the SEPs and how they get into the magnetosphere. So you can imagine we're not quite to the point of having all of that yet.
Janet, there's a question.
Okay.
Yeah, I'm just wondering if you would see all of these effects on spacecraft that are not necessarily around Earth, throughout the heliosphere, or is some of it intensified by specifically being being in the Earth's magnetosphere?
No, I think you would. The only one that I'm most familiar with is Jupiter, where it's even worse, and the radiation environment there is extremely intense. But there's no reason why this is just going to happen at Earth.
So can I have another response to that question, but I
Sure.
also have a question for you, Janet, and that was, so the surface charging and internal charging, it seems like, are they all related to sort of SEP events causing them? Or do you also think there are GCR particles that can break down, give secondaries, that can also affect? So that's a question. And I'm going to kind of make another comment to Gwen's query. It is actually a very interesting question to ask, whether a planetary environment actually modulates the kind of effect. So giving example of Jupiter is very true, because radiation is so much higher there. But I'll give you another example for you to think about, and that is the stereo spacecraft, right? So they are actually not bound to any planet, and they are sort of going around the sun in the interplanetary medium. And stereo spacecraft have actually experienced, we believe, Carrington level storms. and they actually detected it, passed on the information without being heard. Something to keep in mind, and we can discuss kind of this physics of interaction that goes on inside a planetary environment. Thank you.
Yeah, so I didn't mention GCRs, but they definitely can cause the same issues as the SCP events. And I actually worked on an anomaly with the MEDOP satellites where they were sending down images, weather images, to European countries, and one of those instruments was completely destroyed by a GCR. So we had to figure out where they could safely turn on and turn off in order to switch over to a redundant system. So GCRs are certainly an issue. It's a little bit harder for us to measure and apply, I would say. And space weather related changes, just like the large abrupt events, are less likely to happen. So yes, that's an issue, and we're not really dealing with that at this point. But thank you for bringing, oh, I had a question, sorry. So just take a guess. Which one of these issues caused the most reported problems at Earth? Surface charging, internal charging, single event effects, or total ionizing dose? And again, just write it in the chat and maybe Nick can tell me what the consensus is. Nick?
We got, we're starting to get answers in now.
Okay.
So we've got a few answers. So lots of surface charging.
Okay.
I would say about half, just by eye, half are surface charging, and then it then splits between single event upsets and internal charging.
Okay, great. Well, here's the answer. So this is a plot by Harry Coons, who just went through a bunch of different anomaly databases and tallied them up. So this first one is electrostatic discharges, so surface charging and internal charging. And they're put together because sometimes you really can't tell the difference. But if you were to distribute these other ones, probably internal charging would win out here, with SCUs maybe second. So internal charging, that's most likely to happen at geosynchronous orbit. And it's worth worrying about because a typical communication satellite at GEO costs about $250 million. And we have examples of losses. Intelsat 29E was lost in 2019, which they think was related to internal charging. And then there was also Galaxy 15, which I don't know if you guys heard about that one, but it was called the Zombie Sat for a while because they lost the ability to command the satellite, but it was still functioning. So it was just aimlessly drifting through geosynchronous orbit, sending random signals, and people were having to maneuver out of the way to avoid getting hit and avoid getting clobbered by the signal that it was sending. But the challenge here is that we don't really formally track anomalies in any way. And this study was from 1999. And now it's completely different. So the satellite industry, as I'm sure you guys have heard about in the news, I think someone even posted a picture of the Starlink satellites. Everything's completely changed, and the industry has moved to these really large constellations of small satellites, all in low Earth orbit. And it's mostly being driven by satellite energy, internet, and also imaging. So this is a plot. This is actually from 2017 So it's 400 up to 8,000 kilometers. And then each one of these circles are something like 100 satellite blob. But the amazing part is this big silver orb in the corner, which represents the satellites being planned, which at the time was 18,000. And I think it's actually gotten even much bigger now. But for LEO satellites, it's completely different. Internal charging there is not likely because they don't spend a lot of time in the radiation belts. Surface charging can still happen in the auroral regions, but SEUs are one of the big unknowns here because you can, with a big event, you can potentially take out a lot of satellites in polar orbits, and really there hasn't been a significant SEP event since lots of these constellations were launched. So it's a big question about what's going to happen in the future.
Quick question back on that last slide, just about the color index on the, what does green, yellow, and gray stand for?
The yellow is communication satellites, so that would be the internet ones. Green is for Earth observation, so like Spire is measuring total electron content, and then the silver is what's being planned. And again, it's 2017, so this has changed even since then. Okay, so then even if we could knew everything about the environment, we'd still have a challenge because we don't know exactly how the environment interacts with the materials that we use on satellites. So there's a big research effort now to test different materials in the lab, and it's not always clear how new materials and new components being used in space will actually do. And then the final challenge, even if we knew the environment perfectly and we knew how it would interact with our satellite materials, that doesn't do a thing for the guy sitting at a desk trying to figure out what's going on his satellite. So you need some way to pull all that information together and make it accessible to the users. So with my company, we spent some time actually talking to users in the satellite industry about how they do satellite anomaly analysis. And most of them relied on these plots from the Space Weather Prediction Center showing particle fluxes for 3 days, but it's really difficult to be able to do any kind of attribution with just this because it's only 3 days. You can't really compare it to what your satellite saw for the rest of its mission. It's fluxes, so you have to figure out how that translates into those specific hazards. And then this is GEO, so for all those satellites in LEO orbit, this does not really help. So what we found is definitely some anomalies are going undiagnosed. One group called them space monkeys, because if you want to do attribution, it's really still a research project and it requires significant time and expert knowledge. And this is just a quote from one engineer at a meeting who said, "Knowing what we know now, this process should be automated." So that's been my goal, is to try and develop tools that will automate this process and bring all this research together for end users. So again, the challenge in order to actually respond to space weather impacts is you need some physical understanding of the environment, and you need that captured in real-time models or data or both. You need to know how the environment is going to interact with your system, and then you need some way to pull that all together and provide that information to users so they can actually act on it. Okay, so I'm going to talk a little bit about the physics and our understanding of the modeling for each of these effects. And we're going to start with internal charging and the radiation belts, because that's the area where I think we've made the most progress. So this plot here is showing many years of SAMPEX data. So this is time across here. This is L shell, and L shell again is just showing you approximately where an electron would cross the equator. And then the colors are flux, and SANPEX was a polar orbiting satellite. So as it orbited, it would just cut through the very tips of the radiation belts here 4 times per orbit. So just the general overview. There's an inner belt that goes from about L equals 1 to L equals 3. And then an outer belt going from L equals 3 to outside of geosynchronous. And the amazing thing here is just the dramatic changes that you see of many orders of magnitude, which is thought to result from this constant competition between acceleration and loss processes.
Could you just remind us what the L values mean?
Yeah, so the L values over here, it's approximately where an electron would cross the equator in Earth radii.
Oh, okay,
So
great.
It's like radial distance outward. Okay, so we'll talk a little bit about acceleration mechanisms, and I'm just going to give a brief introduction here because we could really talk for hours about this, and I have some review articles on the next slide if you want to learn more about it. But the dominant acceleration mechanism is through interaction with different frequency waves. So particles have 3 types of motion. They are drifting around the magnetosphere on orders of minutes. They are bouncing at a much higher frequency along the field lines, and then they have this really high frequency gyration about the field line. One of the waves they can interact with is ultra low frequency waves. So these are low frequency, low M number waves, and they're mostly created from interaction with the solar wind. So from the dynamic pressure pulses on the solar wind, or from the velocity shear along the flanks of the magnetosphere that causes Kelvin-Helmholtz waves. So the particle, as it's drifting around, can interact with these waves. And the way that happens, there's a little picture here trying to show that. So at the start of this picture, the electric field of the wave is pointed in one direction here. The electron starts out. As it drifts, if it drifts with the exact same frequency of the wave, then when it gets to the other side, it sees the same electric field. So the effect of that as it goes around is to see this constant electric field that accelerates it and pushes it inward. But you can imagine that a particle starting off on the other side of the magnetosphere would have seen this oppositely directed electric field, which would have pushed it outward and decelerated it. So these interaction with the waves pushes electrons inward and outward, and both accelerates and decelerates them. So the effect is really to try and reduce any gradients. So this is just a simulation. If you put a bunch of particles in and you let it interact with the wave, particles will move inward and outward. And then in order to get a net acceleration, that depends on the radial gradient of the electrons. So if you have an outward radial gradient, that wave will still push particles in both directions, but you'll have now more particles to move inward than to move outward. So you get a net movement of particles inward and an acceleration. And then in the same way, if you have a loss of particles at large L and an oppositely directed gradient, say at the magnetopause, then those waves can push particles outward and you get a net deceleration. So the same thing can happen, the same type of process can happen with higher frequency waves, and mostly the waves that the electrons will interact with are VLF chorus waves. So this is the same type of process, but now the electrons, as they bounce along the field line and are gyrating about the field line, if they are moving at the right velocity and have the right gyro frequency, they will interact with the VLF chorus waves in the same way as with the ULF waves. But in this case, the interaction can change the particle energy as well as the pitch angle. If you push more particles towards 90 degrees, then you'll get a net acceleration. If you push more towards the loss cone, you get a net deceleration. And so which way it goes, again, depends on the gradient, but now we're talking about the gradient of the particles in energy as well as pitch angle. And then for losses, there's really only two places the electrons can go. So one is at the magnetopause. So when there's a big storm and the magnetopause gets compressed, these electrons hit the magnetopause, and as they drift around and then are lost to the solar wind. And then the other possibility is that they get pushed into the atmosphere. And in this case, the waves that are most likely to do this are electromagnetic ion cyclotron waves, or EMIC waves. So these are produced by ring current ions when they are injected to create the ring current. It's an unstable particle distribution that generates the waves. They interact with the electrons. The pitch angle gets changed such that they hit the atmosphere and don't come back. So how does this play out during a storm? This is particle flux. Again, this is time versus L shell. So at the beginning of a storm, here's the main phase of the storm when DST is decreasing. So you get lower energy particles injected through substorms and also enhanced convection. I think Dolores probably talked about this. That leads to a decrease, an increase in the ring current and a decrease in the inner magnetospheric field. In response to that, the high energy electrons actually move outward. Some of them will move outward enough to hit the magnetopause. That outward motion will be enhanced even more by that interaction with ULF waves. And then finally, there's EMIC waves from that ring current that's been injected. So typically during this main phase, you see a rapid decrease of the electron flux. And then during the recovery phase, if that ULF wave power keeps going and the VLF chorus wave power keeps going, you'll see an increase, sort of a slow and steady increase. Although not all storms, so here's one that follows where you see the same decrease and nothing happening afterward. So ultimately we want to learn this physics so we can model it and then put it into space weather tools. So one way you can do that is by tracing particles in MHD code. So here you're just putting them in and calculating the drift motion and seeing where they go, which is great for capturing the ULF wave acceleration and magnetopause losses, but there are not the higher frequency waves are not included in MHD, so you don't get the chorus and EMIC wave acceleration. And it's computationally difficult to do these models right now, so they aren't running in real time for space weather applications. So what you do instead is you treat the interaction of the waves as a diffusive process. So the idea here is to, instead of model every little interaction with the waves, you assume that if a particle interacts with a ULF wave, it will randomly be kicked in L shell, either inward or outward. And then how much it gets kicked is parameterized by the wave power. Same thing with VLF waves. So the particles are randomly getting kicked around. And if that's the case, you can describe the evolution with this Fokker-Planck equation, which looks fairly difficult, but all this is saying is that the change in the electrons here is related to this diffusion coefficient, which is based on the wave power, and the gradient in L shell. So this is the piece due to ULF waves. And then this whole piece is due to the VLF waves. And in this case, it's a little more complicated because you're moving in energy as well as pitch angle. But the same basic concept that you have a diffusion coefficient related to the intensity of the waves, and then a gradient that tells whether it gets accelerated or decelerated. So if you didn't follow all that, that's fine. If you're interested in learning more about it, there's 2 really good review papers here that describes them.
Hey, Janet,
Yeah?
before you go on, there was just a question in chat. I think it was from a couple of slides ago.
Okay.
When you were talking about the particle motion, and the question was whether this describes the protons as well as electrons. Is that, Krishna, is that what you're asking about?
Yeah. Actually, when the storm commences, you have mentioned that the electrons will suddenly decrease the flux. But is this the case for protons in the radiation belt?
No, so the protons are kind of a different process here, at least the really high energy protons. So for the ring current protons, the fluxes are enhanced. And the reason for that has to do with the drift speed here. So the electrons are moving fast enough that they will conserve all 3 adiabatic invariants. So this motion is related to the fact that as they drift around, they will conserve the amount of magnetic flux in that drift orbit. So when the ring current gets injected, the response then is for the electrons to move outward, at least the very highest energy component.
Okay, thank you.
And again, if you want to know more, I check out these 2 review papers. Okay, so ultimately then we want to be able to model what's going to happen so we can include this in tools. And you want to be able to do that in real time. So there's a number of different models that are running now. One is the VERB radiation belt model. It's a diffusion model. It's running here at UCLA in real time. They're also assimilating data, so any physics that isn't captured gets corrected by the assimilation, and it's output every 2 hours. So this is kind of ideal for space weather tools. It also has a 3-day forecast. Mei-Ching Fock has a model running at NASA. This is also a diffusion model, and it's running in real time at NASA CCMC, but it's a little bit more difficult to actually get that output and put it into other applications. And then on the European side, there's a British Antarctic Survey model, which is also running in real time at ESA. And then there's a number of different applications for understanding internal charging. So 2 of the big forecast offices, SWEEPC and ESA, have products that are being put out. And at SWEEPC, the big one is the Space Environmental Anomalies Expert System Real Time, or CSERT. And we just talked about all this modeling, but CSERT doesn't actually use model output. Instead, it specifies the internal charging hazard based on statistical correlations between fluxes measured at GEO and those anomaly databases that we talked about earlier. And then Space Storm at ESA, they put out some stoplight charts at several different orbits based on the electron fluxes from this vast diffusion model but you need a login to get in there, and unfortunately, I didn't get that in time to be able to show that to you. And then at my company, we've developed this tool that's called the Satellite Charging Assessment Tool. And what it does is it allows users to come in, they can select their satellite of interest, and we have the full catalog of satellites available. You can put in specifics about your satellite, like the thickness of your shielding and the type of material that you're working with. You can choose a start time and then create a data set, and it will create your custom data set of accumulated charge, or the expected accumulated charge for your orbit, your satellite, your components. And we do that by flying the satellites through the Verb model. And then you get a timeline that will update in real time. And we actually ran this for the Intelsat anomaly and came to the conclusion that it was possible that the anomaly was related to internal charging of lightly shielded cables, Teflon cables. So with internal charging, I think we're in the best shape in terms of understanding the physics, having models running in real time, and then actually tools to use those models. Surface charging is a little bit more difficult because that's related to the substorm particles. So you can still model it with this same diffusion equation, only for the higher energy particles, you can assume that the drift doesn't vary with local time. For the lower energy particles, that's not the case because they're affected by this convection electric field. So you have to add a couple more terms to account for that and keep track of magnetic local time. So there's efforts to update models to include this term and have them running in real time, but that's still a work in progress. You also need some way to capture substorms, which is a bit more difficult. There still are a couple of applications. So the CSERT model covers surface charging as well. So sometimes just the simple statistics is a good way to go. The Space Storm project at ESA also has a model, the IMTIM model, that tries to capture substorm injections and has that same stoplight chart telling you about the hazard in real time. So there are a couple applications available.
Hey, Janet.
Yeah?
One of our students would like to know whether the CSERT model is available for general use.
Yeah, so at the moment it is, oh, here's the website.
That's, that's SatCat. What about the CSERT model at SWIPC?
Oh, sorry. Yes, it is. And I think I have, it's available here.
Oh, okay, great. Yep. Is okay, great. Maybe the student in question can ask more at the break. Are you coming up on a break point soon?
Yes.
Great.
One thing left, and that's SCPs. So I think you guys talked about how they get accelerated. For space weather effects, we're less interested in how the SCPs cross the heliosphere, and we're more interested in where they actually go when they get to Earth. Because whether or not you have an anomaly related to SCPs totally depends on where you're located, because the Earth acts to deflect a lot of those high energy ions. So if you have an anomaly, you want to know, am I in the high fluxes or in the region where they have no access, which depends on the ion energy and charge. And so typically you have high fluxes over the polar caps. And then as a satellite comes down, it will drop to very low fluxes. And there's a couple different ways you can model this. So one is, these are such large gyro radii that you have to go to the full particle motion. So there's some models where you start at 100 kilometers, and instead of asking what can get in, you ask what can get out. So you send particles in all different directions, and whatever energies make it out, you assume that it can get in. So that's being used as a boundary condition for proton impacts at airlines. But it's difficult to do this for satellites because you have to model such a large altitude range, and it's really computationally expensive. So the other way to do that is to run all the particle trajectories at once for different field models, and then parameterize where they will have access. Unfortunately, that doesn't work very well. So this is just an example where this pink line is showing that protons of 58 MeV get down to L equals 4, but then this is what is actually measured. So right now I have a project, a small business grant, to try and do a better job of modeling this proton access regions using actually measured data. And again, CSERT also has a statistical correlation method that tells you the likely hazard from SEPs. So this is my last slide for this section, which is just a question, because right now there's a lot of people working on what should be the new observations, research, and applications being developed. So if you were a funding agency, would you focus on surface charging, which caused significant anomalies in the past? It's challenging to model. We have few applications available. Affects LEO and GEO. Internal charging, which has caused significant anomalies in the past, but we're doing pretty good with real-time models and applications. Really only an issue probably at GEO. Or single event effects, which have caused fewer anomalies in the past. It is feasible to model. We don't really have applications. Doesn't really happen that frequently, but could have a really big impact on the new LEO satellites. So that's a free question for you guys to put in the chat. And then, do you want to take a break, Nick?
Let's get an answer for your question, and then we can go on break. So yeah, take a minute and think about what your response might be to this. You can just put surface, internal, or single event, or single. Surface, internal, or single. So we've got one of each so far. We've got 2 of each so far. Yeah, give me a one-word answer. I'm not going to read a paragraph.
So Bill Murtaugh is heavily involved in this effort to define new observations. Right. I don't think he called in, did he?
I don't think he is, you know, because we would have heard from him by now.
Yes, true.
So surface and signal, it's and single event. So surface charging and single event effects seem to be about evenly split.
Yeah, that's my take as well, and that's why I am focusing now on single event effects, mostly because I'm waiting for the models to get a little bit better to develop tools for surface charging.
And do you think if we did a poll at AGU, we would, or at CEDAR, say, or GEM, do you think we, what do you think we would get?
I think if you went to GEM, they would say internal charging, because that seems to be the interest of the science community, and maybe less so for space weather.
Huh, interesting, okay.
So I have a question. So this is when you say observations, I mean, are you interested in kind of the source population? What is it you want to measure and kind of predict? Basically, you know, are you interested in kind of looking at the energization process in the magnetosphere, or are you interested in actually getting the source population from the sun through solar wind into the system, or both? So I'm kind of trying to figure out.
Sure. I mean, ultimately, you'd want to be able to predict this. I'm kind of more focused on just saying what's happening, doing a nowcast, because we don't have that covered yet. And then I think you'd go to forecast. So I'd say for science, I think there's different things you want to look at than for space weather. So for space weather, I think you want observations to do data assimilation more than figuring out source populations and all that. So
which would be nowcasting.
Yeah.
Like you can't take mitigating steps, but you kind of know what did something.
Right. So with satellites, there are people that are interested in knowing what's coming, but there's not a lot you can actually do to mitigate. So I think the bigger interest is in figuring out what's going wrong. Like figure out if something went wrong, was it space weather, and how often is it going to happen again?
And my other question still is, I know that kind of most of the satellites and sort of computer processors and all that in most of our satellites are kind of from the previous century. There are like significantly different kind of evolution of processors that will be put in future. So question is, what are the impacts that you see outside of this? Or these are the only impacts we know of electronics on computer? Does that come through that line, single event upsets basically? And it's like a catch-all for all of those?
I think the way that the environment will interact is, I mean, that's physics. It's not going to change that significantly. For single event effects, there's a lot of things you do now that can mitigate some of the issues, like having redundant systems and some checking to see if there's any bits being flipped. I mean, there's always going to be new things that I don't know about. So it's hard for me to say what's going to happen there.
Well, you are the state of the art for us here. Thank you.
Yeah, so let's take a 5-minute break. Why don't we be back by 35 after the hour? And we'll start in again and maybe if anybody's got any other questions, Janet can answer them during the break. I think, so Dolores was trying to ask, and she can speak for herself, but can we gain access to, can we run the CSERT model? I think.
Right. I can see the output on the SWPC page, but I was just wondering if students and researchers can actually play with the model and use it.
So the model itself is a pretty simple set of equations. So no, you can't actually get it. You can't even get the output in numbers from it from SWPC. You can only get those plots, and those plots aren't archived. So that's an issue that SWPC, I think, is working on. But I don't know if I put the reference for Paul O'Brien.
Yeah, he had a paper in 2009 or thereabouts.
Yeah, there's a paper on it. If you go to this the NOAA website for CSERT, that paper is listed there.
Okay.
And you think
Yeah,
it's,
I was trying to use that as an exercise in the space weather class that I teach, and all of a sudden I go, well, I can get nice plots from yesterday, but that's it.
Yeah, yeah, there's no actual model, but it is pretty simple to code up. It's just a set of equations. The only difficult thing is, well, that's not even difficult. There is a mapping of the electron flux, the high energy electron flux at GEO for internal charging that's done. But pretty straightforward.
Okay. Thanks, Janet.
Sure.
So I have a question. So aside from building like radiation or better radiation hardened satellite, what can like the satellite companies or a satellite operator actually do to mitigate damage? If you were able to forecast such an event on short-term notice?
If they really believed it was going to be a significant event that would take down their satellite, they can put it into a safe mode, which is like really minimal operations, which could potentially minimize some of the risk. But I don't know of anyone that has actually done that.
And the second one would actually be about like the private industry part. So all these models I assume are all like provided by the government. So do you see like the private component more as being like basically combining all the information and digesting it for the actual satellite companies, or like also going into like private research in that sense?
Well, let's take a step back because the government is not providing, well, I guess the NASA one is being provided by the government. Verb is not, it's being run at UCLA. And there's actually a commercial business. So Yuri's group has an LLC, and they are now trying to operationalize this for the Air Force through a small business grant. So they are trying to make this an operational model, but through a small business. So I think it's really, in this case, it's both. I would think, my personal opinion is that it would be more useful to have the government focus on running these big models and putting the data out so that commercial companies like myself wouldn't have to deal with that part. And I think they have certain advantages in that they can probably get more data sources than commercial groups could. And so they might be better situated to actually run these models. And if they did, then it would just simplify the process and you could have a proliferation of different tools based on that. So that's what I think probably is a good model. But there's commercial companies doing all aspects now. There's commercial companies that are measuring data, and there's data buys from the government for commercial data. There's commercial companies, again, building these models, and there's commercial companies building applications. So it's kind of in every part of space weather.
Janet, do you need to take a break or do anything?
No, I'm good to go.
Okay, excellent. If you are back, please turn on your video so I can see that you're back. Okay, we've got about a third of the people back. All right, why don't we get started again?
Okay.
And Dana, are you here? Nope, Dana's not here. All right, so I'll be monitoring chat and questions again.
Okay, so we're going to move on to another issue for satellites, and that's satellite drag. And Tim said he touched on this, so hopefully this isn't too repetitive. But the big picture issue is that space weather increases energy input to the ionosphere and thermosphere, which in turn can increase the height and neutral density, which then increases drag and causes uncertainties in satellite trajectories to the point where sometimes satellites get temporarily lost. Okay, here's a question for you. Raise your hand if you are working with CubeSats, and I think there's a little button next to your name to raise your hand, and Nick can tell me the response.
Looks like only one.
Okay, well, you and the rest of the world are part of the problem here. So, as I mentioned, the satellite industry has completely changed and everything's going to these small satellites and CubeSats in low Earth orbit. So at the moment, there's almost 3,000 operating satellites. Those are mostly US satellites, and they are now mostly in low Earth orbit. And this plot over here is just showing you the countries that had satellites in 1966. And there's a few that you can see there, but now this is 2016 and most countries have satellites. And there's this cool movie. I'm not going to try and show it, but if you want to watch the Earth slowly get all fuzzy with satellites, there's a link here. And I mentioned 18,000 satellites, but now we're talking about 57,000 satellites planned through 2029. And there's not just satellites, there's a lot of debris out there. So this is number of objects versus time. This blue line is satellites. The pink line is debris, and none of this really includes any of the new small satellite constellations. So this was, I took this straight from a talk by Mark Matney at NASA of what kind of stuff is out there from a meter to a millimeter. And the DoD has a space surveillance network that actually tracks and catalogs all this stuff. And you can see that it's slowly increasing over time. There's a sudden jump here. This was the Chinese anti-satellite missile test where they exploded one of their weather satellites. And then this smaller jump was a collision between an Iridium and Cosmos satellite. So space junk is continually increasing. And the worry is this Kessler syndrome, where the idea is once you have a certain amount of junk out there, then collisions become more frequent to the point where it just makes more and more junk, and it's just a cascading process. So NASA has a program that will simulate how much junk you'll have in the future. So this is the number of objects versus time. And without doing any kind of post-mission disposal to try and get rid of some of this stuff, that's the red trace here. The junk is expected to just continue till it gets to 330% in 200 years. So it's a while, but it's still a concern. So in order to not make that problem worse, we'd like to be able to calculate the location of the satellites and make sure that there are no more collisions. And you do that with this drag acceleration equation here, which has a number of different terms, but one of the biggest uncertainties is the neutral density. And I thought Tim was going to talk about this, the physics of the neutral density today, but I think he'll talk more about that tomorrow. But you can get changes due to changes in the UV and EUV light, Joule heating, and particle precipitation. And Tim's really the expert here, so I'd wait till tomorrow to hear more about this. There's a number of different models that are being used for calculating drag and satellite trajectories. Most of the ones being used for drag are semi-empirical models where they infer densities based on changes in satellite orbits and then parameterize them by different solar indices. So there's a couple listed here. Those are more simple to run than some of these physics-based models, which potentially could be more accurate, but not easy to run for 59,000 satellites. There's one commercial model by Astra called Dragster, and this is now using an ensemble of the TIGCM and NREL NSYS to figure out the neutral density, but then it also includes a simulation of errors in measured satellite location to improve it even further. But there's actually a really big commercial interest in tracking satellites. You can imagine with 59,000 satellites being planned. So there's a couple of groups that are working on this, which I wouldn't call these space weather groups. These are just industry groups. And one is AGI, and they've actually developed their own commercial space operations center, ComSpock. So it used to be the Air Force, JSPOC, that tracked satellites. Now they're actually doing it at a commercial company. So they've got telescopes, radar systems, and RF sensors, and they are tracking satellites themselves, as well as providing commercial users with things like conjunction assessments to make sure there aren't any collisions. And then there's another group called the Space Data Association, and they are doing a similar thing. They don't have a ComSpock. They aren't actually tracking satellites themselves, but they use public information to figure out trajectories. And then in addition, if you join the Space Data Association, you agree to contribute your more detailed information about your satellite location. And then they use that information from the people who are members to try and come up with even better conjunction assessments. So there's a lot of interest in this. I'm not even sure what satellite drag models they are using. I think AGI has actually developed its own, so there's a lot going on completely outside the science community.
So Janet,
yeah.
Couple of questions, or well, so there's a commentary in chat about the issues with a space war, but then the question, aside from collisions, what's the other source of space junk? And I'm not sure what the second sentence means, Jeff.
Well, there's collisions, and then there's stuff that just hasn't deorbited.
Right. So I know that the FCC, I don't know how this might work for other countries outside of the US, but the FCC has a requirement that you can prove the ability to deorbit your spacecraft, or itself will deorbit within some period of time, or they don't let you launch. And then the second part of the question is just, isn't this case improved by using increasingly smaller spacecraft, just from the perspective of there's less stuff to then become junk?
Well, if there's 59,000 of them, I don't know if there's less stuff to become junk. And I don't know, we'll just have to see how it plays out. I don't know what regulations are out there right now, or if all this stuff is from before there was regulations. I'm not quite sure. But I don't know, there are some benefits to having small satellites, but 59,000 of them is a little bit difficult personally for me to wrap my head around and figure out what's going to happen in the future. These models, I should say, I don't know if I mentioned this, didn't even have small satellites in there, and certainly not 59,000 of them. So I think it's actually just a big unknown at this point.
Sure.
And then there's the question of, if we have a big SEP event, and a lot of the companies putting stuff up now are newcomers to space and are not super informed about space weather. So potentially we could have a lot more unintentional space junk, which is something to think about. So my summary is really short. The number of objects in space is continuing to grow. And I think inevitably there is going to be a need for better modeling and predictions. So if there's not any questions on that, we're going to go on to power grids. Okay. So the really big picture issue is that space weather can cause ground-induced currents, which ultimately can cause large-scale power outages. That's the really simple picture. This is a little bit more detailed. So most of the large power grid issues are associated with large CMEs. So you start with the CME. The impact of the CME at Earth creates a number of different current systems, all which close through the ionosphere. So when the CME hits, it causes a dynamic pressure increase and a sudden storm commencement that can increase some of the dayside currents. That's generally followed by a storm, which enhances convection and increases these region 1 and 2 currents. And then substorms, which can really happen just about any time, but those are going to cause night-side currents through the auroral region. So ultimately, these currents in the ionosphere create a changing magnetic field, a DBDT, that you can measure on the ground. And it's that DBDT that creates an induced electric field at Earth's surface. That induced electric field creates potentials across power lines, usually these very long power lines connected between high voltage power lines between different grid pieces. And it's that current that gets produced there that can cause problems for the power grid. So the issues are that the GICs interact with these high voltage transformers that connect the long distance transmission lines to the grid. And here's a simple picture of what these transformers look like. So you have a wire wrapped in a coil. Since we have an AC system, this is creating an alternating magnetic field. That alternating magnetic field creates a potential over here. And then the difference in the potentials depend on the ratio of those coils. So when you get a DC signal coming through here, you get a DC signal in this, or an offset in the magnetic field, this oscillating magnetic field being created over here. So you go from this nice sort of sinusoidal thing to something that's offset. And they call that half cycle saturation. And it's this offset magnetic field that then can create harmonic signals in the grid. And one of the biggest issues, well, not the biggest, but one that has actually caused blackouts is just the fact that when you have all those harmonic signals, it can trip protective equipment and then disconnect parts of the grid. So that's actually what has caused the 2 known space weather related blackouts. The other issue that people used to talk about a lot, and maybe seems less concerning now, is that those harmonics can cause heating or incremental damage to the transformers. And I don't know, 10 years ago or so, people used to talk about losing hundreds of transformers and they take, you know, several years to build, and so we could be in darkness for 100 years. I think people have really backed off from such dire predictions, and the industry at least is less concerned about this problem, because to melt a transformer, you need to have really sustained heating, and they're pretty confident that these protection systems will trip before that happens. Nonetheless, the Federal Energy Regulatory Commission here in the US has identified 30 high voltage transformers that they say are critical, and if you lose 9 of those, that could result in a coast-to-coast blackout. And then the last problem, which the industry folks say is the most concerning, and it's the one. Sorry.
Janet, can I ask you a question on the previous kind of your point that you made, that the industry has kind of backed away from that kind of rhetoric?
Yeah.
But how is it that we see that in the government, you know, that is kind of generating swarm type documents, that these, including, I think, and if Bill is there, Bill can talk to it, including NOAA, kind of still uses this as being one of the primary drivers of space weather impact.
Is Bill actually there?
I don't know.
I don't think he's there.
Okay.
But NOAA commissioned a study by ABT on space weather impacts and the economic impact, as well as user needs. And in that report, it specifically, I mean, they went and talked to a lot of users or industry people about what the issues are. And my saying that this is not the biggest concern is straight from that report. So I can't really answer why NOAA might be focused on that.
Oh, I'm talking, I actually attended a space weather architecture discussion, which is interagency, and it is being kind of directed from the NOAA satellite division. And this still seems like a big deal from what I heard during that meeting, but very interesting. And this is available, this ABT Associates report?
Yeah, I have more on it in the next couple slides.
Thank you. Thank you.
So at least from the industry discussions captured in this ABT report, and maybe not everyone agrees with this, the biggest issue, at least to the power grid industry, that they think is this reactive power absorption. And I can't say that I can really describe this well at all. But somehow you get oscillations in the power grid, which eventually leads to this voltage instability and a power outage. So if there's going to be a blackout now, they think it will be related to this, and that these issues with tripping protective equipment are not as concerning, or the issues with the meltdown. Although I have to say, Lika, I talked with my USGS colleagues about this, and I said, you know, we all see this picture of this melted transformer, so if it's not going to happen, then why did it happen here? And I don't have a good answer for that. So the two big events where power was actually lost, one was the March 1989 Hydro-Quebec power outage. And there's a nice paper that goes through all the different impacts here. So it started with a very large sunspot group that was one of the most active sunspot groups from March 6th to the 18th. There was 19 greater than M5 X-ray flares. There's no solar wind data available for this event because IMP8 was not in a place to observe it. However, people have tried to back out the number of CMEs based on ground magnetometer data and the flares, and they think there was 2 ICMEs at 760 kilometers per second and over 1,000 kilometers per second. There was a large magnetic storm that ensued, which was the largest that I think we've been able to measure with the stations that actually make up DST. So it's the largest well-measured storm. And then at the time of the blackout, there was a large substorm current signature. So that's thought to be the cause. And in this case, the power system went unstable and protection relay shut down the system. The blackout lasted 9 hours and affected 6 million people. And it destroyed that transformer at the Salem nuclear power plant in New Jersey, but apparently there was no blackout that resulted from that loss of the transformer. But this was a big one because until then, I don't think the impacts to the power grids had really been fully appreciated. And then the next one was during the Halloween storm. So this was a series of solar activity that lasted from about October 19th to the 5th. On the 29th, there was 2 CMEs that hit. And the first one of these caused this 2-phase storm. And I think Dolores talked about this yesterday, where the first CME sort of clears a path for the second one, which can then be even more impactful. Oh, sorry, I apologize. That was not true. So this double storm was not one of those 2 CME events. This was actually the first CME caused this double storm. And then there was this just 1 dip storm following from the second CME. There was a number of power grid issues that were observed, but the power outage happened at this second one. And again, it's thought to be caused by these harmonics tripping the protective equipment. And in this case, it was 50,000 customers without power for 1 hour. And just a quick estimate of the losses just from the unserved electricity, meaning you're not selling that electricity, so you lose that money, not necessarily the impacts to all the users, was estimated to be $500,000 in US dollars. So of course the real concern is if we have that with the, well, big but still not huge storms, what happens when you get one of these superstorms? So most of the focus is on this Carrington 1859 event, which was one of the largest flares in the top 100 ever observed. DST, we didn't have all the stations to measure DST, so it's been estimated at being somewhere around 900 nanotesla. And there's all these really great stories about aurora being so bright that gold miners in the Rocky Mountains got up and started making breakfast, or the telegraph lines sparking and unreadable messages coming through the telegraphs with atmospheric fireworks and brilliant sparks. There's been a number of studies to estimate the risks of another Carrington event. One by Pete Riley that was at 12%, and there's another more recent one that puts it quite a bit lower. There's another storm that happened in 1921, which some are now arguing could have been as big as the Carrington event, and Jeff Love has an interesting paper where he went back and dug up some old records and reconstructed a DST to be at 907 nanotesla. And that one had some of the lowest observations of aurora all the way down to Samoa. And then, I think you mentioned this July event that Stereo saw going off the backside of the sun, which a number of people have estimated would have created a Carrington scale event had it been directed towards the Earth.
Yes, I have a question. When people actually create probability matrix and say this is kind of the probability, I mean, that's kind of based all on Earth-facing observations, right?
Yeah.
So how do we create a probability for a sun that's spherical?
Well, I think the concern would be if it actually hits the Earth. So I think we're okay with that.
Well, that just kind of, from the physics point of view, it doesn't make sense whether the sun produced Carrington event, you know, that is at an angle. But then, because that's not the question we were asking, I think, right? We're asking, can the sun, how often does the sun produce this? And anything in its path then is going to experience it. Because we can't predict the where on the sun this will occur. At least that's how I think about it.
Sure. Well, yeah, these estimates are based on what's going to hit the Earth. And for space weather, I think that's going to be the major concern. And that's going to be a much more difficult to ask question to answer how often the sun actually does that. Don't know that we'd have measurements to do that. Okay, so in any case, this is the...
Hey, Janet, before you move on.
Sure.
One question from a student in chat about the latitude dependence of power grid impacts. Is it more pronounced at high latitudes?
We'll get there in a moment.
Great.
A number of slides down and some physics and other stuff that we have to get through. And that's actually a question I will have for you guys. So hold on just a little bit. So the economic impact. So I mentioned this study. This was commissioned by NOAA, and I apologize for, I know this is an international group, and this presentation is totally focused on the US because that's what I know. So there are certainly other countries interested in this, and this will be a global issue, but this is all US work. So NOAA commissioned this study by a group that went out and talked to the power grid industry about the issues and estimated the costs. And they looked at two things. So one would be the cost just to harden the US power grid against these types of problems. And they came up with a number from 50 million up to 1 billion. And that was based on two things. So one was, there's about 2,000 of these high voltage transformers, and 1 to 10% of them they think would be vulnerable because of just age and degradation. And to replace all those transformers would cost about $1 billion. The other option people have talked about are these GIC blocking devices, which cost about 500,000 each. So you could put those in place, but one of the concerns there is you solve the problem there, but potentially just push it somewhere else. So it's not clear that this will actually solve the problem. And then they also estimated what the cost was from service interruptions from a blackout. And again, came up with two estimates, anywhere from 400 million up to 10 billion. So they base these off of two types of events. One would be a moderate 1989 type event that was 6 hours over just some portion of the US, and then a longer 9-hour event over a larger portion of the US during peak hours. And they did this using this calculator online, and I didn't get into the details of what goes into this, but you can actually look at this and you can do things like put in the number of people and where they're located and how long a blackout is, and it will spit out a number for you. So I'm sure it's very complicated and includes a huge number of different impacts, but that's kind of fun to look at. So the impacts go anywhere from 400 million to 10 billion for one of these bigger events. Okay, so in the US, recognizing that this is potentially a very severe issue, they created the Space Weather Action Plan. Lika, you probably know more about this. which called for the definition of a number of benchmarks. And for the power grids, they were looking for a benchmark that would give the 1 in 100 value of a theoretical maximum of the induced electric field at the surface of the Earth, which is something the power grids could actually work with to understand the vulnerabilities of their systems. And they've come up with a median value of 0.26 volts per kilometer. There's no theoretical maximum that was defined, but the work for this is still ongoing. Okay, so here's more of the physics of what's going on. So we know there's these dB/dTs. We want to be able to figure out what the induced electric field is, and you can do that using Maxwell's equation. So we'll start with just the really simple picture that Earth is a conducting green slab. So you assume that the magnetic field has a time variation that looks like this. And from Maxwell's equations, if you take the time derivative of this, you get this expression here. We want to turn it into this diffusion equation, and you do that by taking the curl of both sides. So you get on this side, del squared is equal to minus I omega curl of B. And if you substitute this back in, you get this expression here. And if you assume the conductivity of the Earth is constant, and there's only variations in the Z direction going deep into the Earth, you can solve this to get the electric field. And you find that the electric field if it's E0 at the surface, then it will exponentially decrease with this skin depth that's dependent on both the frequency and the conductivity. So now if you take this solution and you plug it back into our first equation, you get a relationship between E and B. And if you didn't follow all that, that's fine. There's a paper here that you can go back to that goes through all these steps. The important thing here to see is in this simplified model, what you find is low conductivity regions result in large induced fields. High frequencies result in large fields. And then of course, if you have a large dB/dt, you get a large E. And in this 1D constant conductivity approximation, E is always perpendicular to B. Of course, we know that the Earth is not a constant conducting slab. There's a ton of variations. But instead of trying to model this by creating some really very complicated structured conductivity, instead what you can do is just measure that relationship empirically. So there's a project called EarthScope, where what they did was put out magnetometers and electric field measurements so you could get both at the same time. They did it in a 70-kilometer grid spacing. You let that run for a few weeks, and then you can actually derive the impedance or this empirical relationship between E and B across the US. So this is what the map looks like currently of where they have these measured E and B values. So now in the one-dimensional case, the relationship between E and B is simplified. We've gotten rid of these cross terms in the impedance or the relationship between E and B. Now in this 3D model, we actually have these cross terms here. And again, these are measured, so it's a fairly straight method for coming up with the induced electric field. It sounds like it's simple, but actually coming up with these impedances is a little bit more difficult because the electric field measurements especially are very noisy. This is just a quick little movie that shows you the effect of the 3D impedances. If I can get it to start. So this is an oscillating DBDT. If you didn't have any 3D conductivity, the electric field would just sway back and forth. But now that you've added that, you get electric fields going in sometimes unusual directions. And then this is a paper by George Lucas and others at the USGS just showing the difference between the simple 1D conductivity model shown over here, where all the arrows are going in the same direction and there's just a difference in their length, versus this more complicated 3D model where now you can get electric fields, much larger electric fields, and going in all different, maybe unexpected directions. So then ultimately what you want to do is figure out the potential that this creates across the power grid field lines between these transformers. So first you have to interpolate that electric field that's that you have at all the earthscope stations, and then calculate the potential using these models of the power grid. Okay, so here is the question for you all. So we know that these large E fields are associated with low conductivity and large DBDT. And this is sort of the statistical equatorward boundary of the aurora that you'd expect over the US. So you expect the intense DBDT to be at high latitudes. However, we also know from conductivity maps now that there's very low conductivity regions at low latitudes. So out of these two regions, which one do you think will have the largest E during an extreme event? This box 1, where you're at high latitude but high conductivity, or box 2, where you're at low latitude and low conductivity? So maybe you can just write 1 or 2 in the chat and Nick can tally up the results.
I'm counting on my fingers. So we've got about, well, let's get some more responses, about half people responding. So this is a 1 or a 2 in chat. And if you don't know, make a guess. It's not quite a coin flip. I would just eyeballing it. It's about 60-40 for 2. So 2 gets 60% of the votes.
Okay, good job. That is the answer. So this is another paper by Greg Lucas where he's estimated the 1 in 100-year electric field at different locations, which are shown here. So in this high conductivity, high latitude region, you actually don't see very large electric fields, whereas all along here on the east coast of the US, that's where the bigger hazard is. So to do this, they identified 84 large storms in a 30-year period. It was based on large DST and also large KP. They used the measured V and this empirical impedance to create time series of electric fields for each storm. And then they used extreme value statistics to take that to the 1 in 100 electric field. And this is what they come up with. So far, it's the East Coast that has the highest hazard, although you can see that there's a large region that has not been mapped yet. And I think there are plans to go forward with that, but I don't know when that will happen.
So there's a question in chat, does this normalize for the system capable of being affected by storms? So Jeff, why don't you just say it out loud?
Yeah, sorry about that. I typed that the wrong way. I was just curious if this prediction system normalizes for the density of systems that can be affected by these kinds of storms. Like, are there more ground systems in the southeast than there are in the northwest, essentially?
Yeah, that's a good question. And I didn't put the plot in here, but he took it a step further and then actually calculated the potentials across the power lines. And it still ends up being this East Coast that is the high hazard region. So yeah, Lucas 2019. So I'd refer you back to the paper if you want to know more about that.
Thank you.
Okay, then what's actually available for power grid users to understand these impacts? So SweepC now provides real-time movies of this USGS geoelectric field using the 3D conductivities, which gives you a nowcast, but for the power grids, you really want a forecast, and the operators have asked for at least 3 to 6 hours to be able to respond and do something about it. And of course, you could do some machine learning type techniques, but one way to be able to forecast is with a DBDT from the physics-based models. So SweepC has implemented the University of Michigan's geospace model, which is now running in real time, and you can get these movies with plots of delta B. And at the time I grabbed this plot, there wasn't much at all going on. And there's now, obviously the ultimate step would be able to take that to the electric field still, and then straight to the power grid. So there's a very large project sponsored by Los Alamos now to try and improve the models so that they have a chance of actually predicting these large events. So they're making improvements to this, all the coupled models in the space weather, now I just blanked on what that stands, space weather modeling framework. And they're going to try and simulate very large storms so that they think they have an accurate representation of these Carrington storms. They've included some data assimilation in the space weather modeling framework, and they're also working on running ensembles using different realizations of the solar wind, which has some pretty interesting impacts on the final electric field that you come up with. And then lastly, they've already developed this power flow solver, which can then take that and apply it to a network of the power grid. So that's all I have. If there's any more questions, we can jump to that.
All right, let's thank Janet. Okay, great. And questions for Janet. We'll take a couple of questions and then we'll give you some instructions and then we'll transition into office hours. Okay, Liz, you want to just say that out loud?
Yeah, sure. So I'm just kind of curious. So, because I noticed that another area of low conductance was also northern Minnesota, where I know there's a lot of like basalt bedrock and things like that. So I was just kind of curious if you can map those low conductance areas back to like bedrock patterns.
I'm sure you can. That's not something I know anything about though, but I know that's, I mean, the reason they're doing this at the USGS has more to, well, partly it's for space weather, but there's an interest in the geologic features, which I know nothing about.
I can't give you details, but yes, I mean, it's not, you know, how the electric current flows beneath the soil. It's very much also a function of conductance. There's a latitude dependence because of magnetic field. There's conductance. Who knows what other parameters also will be, you know, unveiled in future.
I think in the past they tried to create more complicated sort of layering models of conductivity based on the Earth's structure, but really just measuring empirically seems to be a simpler way to go about it and more accurate. So.
Other questions for Janet?
I have a quick question. I got that last question wrong. I guess I could have read your bullet points a little bit more closely. How low conductivity creates low or high E fields. But low conductivity means high resistivity in the Earth. So I'm assuming that's the driving mechanism for having a high E field, is that it can't penetrate to the Earth, so it finds different, you know, I guess power grids to exist in. Is that kind of the right mechanism, or am I getting this mixed up?
No, that's my understanding. And if you got it wrong, don't feel bad, because you can't really. Just based on knowing that it's low conductivity or high B doesn't tell you the exact relationship. I just thought it was kind of surprising that just from the space weather point, I would assume that you would have the biggest hazard up at high latitudes. And before we really knew much about these conductivity structures, I think that was the basic assumption. And people used to try and indicate the hazard using KP or even local K indexes, which really doesn't capture it. And you have to include this conductivity structure to know what's going on. So that was the main point of that. You couldn't really get it. I mean, if you got it right, you're a good guesser. There's no way to know it without measuring that stuff.
Thank you.
You were in fine company, Will.
I have kind of a question, more of just a thought piece, but I'm curious to get your feedback on it. I know that one of the challenges in trying to understand the riskier areas lies in the fact that a lot of power companies don't want to disclose information about their systems and some of the effects that they've already experienced through various features, you know, whether it be space storms or something larger or even smaller. But I'm curious if you've thought about ways to, I don't know if mitigate is the right word, but to address understanding their systems more without the company's help.
I think it's probably difficult to understand without the company's help, and I think at this point we're kind of relying on them to figure out what the impact then is to their systems. And you're right, people don't necessarily want to share all that information or reveal what kind of issues they've had. But I just was talking with some folks at the USGS, and I think they're going to have a paper coming out soon that actually shows the location of different issues. And it's kind of interesting because maybe I can pull this back up. Where you seem to, it's still covering. Where you see the issues does seem to be in the regions that have been identified as a hazard, but that's kind of a problem in all areas of space weather where, you know, to really understand space weather, you need to know the impacts, and it's not, people don't always want to talk about that, although I think more people are willing to share that information than they have in the past. And I mentioned with the satellites, we don't track where satellite anomalies occur. We once had this vision, it was actually in the Space Weather Action Plan, to create this satellite anomaly database. And it completely failed because nobody was willing to contribute, not even the government agencies. not even our own government agencies. So it's a challenge.
I guess that kind of sparks a secondary question then is, where are the majority of spacecraft coming from? Is that a private industry, universities, military, government, that sort of thing? Because that's obviously a big factor in whether or not we can have information that's useful for things like what you're talking about today.
I don't know the breakdown. I don't think that was shown in any of my plots. I think it used to be military, and now it's definitely more commercial with all the small satellites. But so again, with the satellite anomaly database, our government, the U.S. government, asked for in the Space Weather Action Plan had an action to create an anomaly database, and our U.S. government would not contribute the anomalies. So I don't know how.
Not frustrating at all.
No, not at all. So it's a challenge. Yeah.
Thank you.
Sure.
All right. Why don't we, so got one instruction for you for your time zone groups. So we've got one more lab for you to work on. It's the ionosphere lab. For your time zone groups, so you work through the first part. Don't go into the group work. We'll save that for the synchronous groups tomorrow. So I think there's some features that you want to use. This one is purely uses the CCMC interface, so it'll be a web interface, and so the bandwidth issues will be won't be an issue, and we shouldn't have any of the other difficulties that we've had with this. And so get used to that interface, learn your way around it as you're doing the first part, and try and understand the vertical structure of the ionosphere. And so our primary question or primary learning goal for that is to understand where the different layers in the ionosphere come from. And then I'm sure Tim will have a few things to say about that tomorrow. And so that's the only instruction for the time zone groups. So does Dana, Tammy, we got anything else? Tammy wants to remind us about something, pictures?
I do. Please remember, those of you that have not submitted your pictures with the headshots to me, please send them to me so we can get that taken care of.
And some of you have had headshots in there that are like from the nose up. Are those okay, Tammy, or do we want a full headshot?
You know, there's a few of them that I'm going to ask to resend.
Okay.
When you kind of hover over them a little bit, you can get the whole face. So
I see.
We'll see how we can make it work.
Okay, great.
Hey, is this true for all of us or for the students?
I'll take yours too, Lika.
I have a headshot in there somewhere.
Just a quick question. So the photos were supposed to be made from the webcam?
You can make them you can use any headshot. We're going to try and compile a collage.
Yes.
So you can use any headshot you want.
Because normally we would have the whole group together and we do this great picture of all of you. And so needless to say, we are not all together in person. So we're going to try and figure out how we can at least get the whole group picture together. So if you would all please, yes, whoever has not sent me theirs, please send it to me. Okay? Thank you.
Okay. Any other announcements? All right, so we're going to transition into office hours. If you've got questions or want to listen to questions with Janet and Tim. Tim's still here? Tim's still here. Then great. If not, we're done for today.
Okay, so I have a question which is more about yesterday, but I think Dolores is still here. And this is regarding the slot regions. So yesterday a theory was brought out that you have the, I can't remember exactly which frequency band it was that was interacting with the particles in the slot region and basically clearing it out. But if this is the case, could you basically produce different kinds of waves that would be able to like clear out the other Van Allen belts or increase the size of the slot regions?
I can answer that, and the answer is yes. And there's people who have really been looking at that possibility.
Yes, and I wanted to chime in with the same answer.
So can you like get rid of it completely, or is there some limit to how you can basically depopulate those areas of particles?
Dolores, do you know the answer?
I think that there are certain energy bands that are being targeted. I doubt that you could eliminate the entire belt, but you know, if the belt were somehow enhanced, I think there's some effort that was being made in the past, and I don't know if it's still ongoing, about seeing if you could reduce the flux to a level where spacecraft could survive.
So the fluxes that are too high for a spacecraft to be there are basically in a permanent orbit.
Right. So you know, it's a question of could a nuclear detonation make a region of space unusable because of the extreme enhanced fluxes, and there's been a concern about that, and so then an effort to find out, well, could you mitigate that?
Well, on the topic of like nuclear explosions within the magnetosphere, I actually got into an internet argument with someone once where they claimed that basically the particles would stay there for years. But as far as I know from everything that I've learned about the magnetosphere in the past year or two, is that these, like the fluxes would like drop significantly within a few days, if I remember correctly, or is that not the case?
That's not the case at lower altitudes and lower L shells. And I mean, part of space physics and why the interest in particles came up was the starfish explosion. And people started madly calculating how long that would last. And at lower L shells, it's very slow decay and very long lifetime. So in the outer radiation belts, it's not quite like that. But the inner belt with the protons, it's a much slower decay. Would you agree with that, Dolores?
Yeah, I would. Yeah, so one of the big concerns with the extreme event in, I think it was March and maybe then again in June of 1991, was that particles were had gotten into the inner belt by very natural processes and very, very quickly. And those took a long time to decay. Now, those may have been more electrons than protons, but it was a real awakening to realize that nature could suddenly populate a belt with, in this case, I think it was energetic electrons in the inner belt within 3 minutes. And so lots of interest to find out about those kinds of things and what you might do about them.
Yeah, I think there was a paper by Yuri Shkretz where he modeled that, and you got this, tried to model a severe storm and got the increase in the high energy inner belt. And then he actually calculated new satellite lifetimes and saw a significant decrease in the lifetime of a lot of the low altitude satellites just because of that enhanced radiation.
Right.
Okay, thank you.
I just have a question on the space travelers and the astronauts who are in International Space Station, as well as for the Mars missions that are in plan. So how are these energetic particle radiation and single particle effects? Those are being taken care.
I don't know that they have been taken care of. I can tell you about the International Space Station, and there they only infrequently will touch through the radiation belts, or possibly, I mean, they're concerned more about SEP events. And they actually watch the NOAA website and make sure that astronauts aren't outside of the station when there's some big event going on, or have them get to a more protective area. And for the plans to go to Mars, I don't know that they have solved that issue. And there's also just the galactic cosmic rays, which are there all the time, and much heavier, and could possibly be a bigger problem.
So very true. And that's why I was asking earlier, Janet, the question, you know, when you're solving kind of issues in geosync where there are, you know, trapped particles and SEPs driven, accelerated electrons, etc. That's kind of one set of problems. If you are actually in deep space outside of our magnetosphere, you are actually experiencing different kinds of population. And then that's where forecasting becomes really important. With galactic cosmic rays, it is more climatic variation. So it's like, you know, over a long period of time, you know, the variation of galactic cosmic rays goes opposite to the strength of the solar magnetic field, because these particles are coming from extrasolar system, basically. So during solar minimum, you have a high threshold of galactic cosmic rays, which can be really pretty lethal, because these are higher, you know, ionizing ions, basically, which can cause more damage to human health. But electronics is yet another area in deep space we have not talked about very much, especially with the new kind of you know, devices we might be flying. With SCPs, the issue becomes is that you really have to do forecasting given how rapidly they travel. So you have to know, you know, if a particular region is going to produce SCPs, and that's a physics question which is not solved, but you know, people are looking at it. AI ML tools are being deployed with the limited amount of data we have to address that. One of the things that the Johnson Space Radiation Center, that kind of looks after the astronaut health, what they look for are signatures of all clear situation where, you know, with certain level of confidence, you can say that such an eruptive event will not occur. So that's kind of where we are.
Thank you.